Good evening. So clear me once the audio and video. Is it clear for everyone? Okay, right. Okay, right. In the last class we started losses in transformer. So the losses, the major losses are iron loss and copper loss, also called constant loss and variable loss. And the minor losses are stray load loss and dielectric loss. So generally we neglect that minor losses in all our calculations. We never consider. Only iron and copper loss we will consider in the calculations. Okay. Now, first we have seen, after that we have seen tests on transformer, and tests are mainly four types. That is mainly four types we conduct in the lab, and there are many tests if you go to manufacturing side. So the main four tests are what? Polarity test, OC test, SC test, and Sumpner's test. So previously we have seen in last class polarity and OC test. Okay. So there I have given in the last OC test these two important points. In a transformer under no load, first one is in a transformer under no load test, by keeping voltage constant, if the frequency decrease, then no load power factor of transformer is dash, decreases. So how it is? Initially we considered some voltage V1 and some frequency EF. So with respect to that voltage and frequency, we have drawn no load phasor diagram first. Okay, this black colors, I mu, this IW, and I naught. So whatever these black letters, I mu, I naught, IW. First, initially there is some no load current with respect to some voltage and frequency. After that, what we did, now whatever change given, what is the change in the first point? Voltage constant, frequency decrease. So that is we applied here. Voltage constant, frequency decrease. So whenever frequency decreasing, the flux density what happened? Increasing. So already with respect to rated voltage and frequency, that is under maximum density. But when frequency reduce further, then it will be beyond maximum, which is under saturation condition. So under saturation, always the current, magnetizing current demand from the source is very, very high. Okay. It will demand high magnetizing current, like I drawn like this. What is the variation of flux and current? I mu is creating flux. So if you consider the magnitude of this I mu and flux relation, it will be like this. See, whenever current increase, flux also increase. Whenever current increase, flux increase, current increase, flux increase. So it will take place linearly up to a particular point, up to maximum flux it reaches in the core, maximum flux. So this is the corresponding rated magnetizing current, I mu. But after that, once maximum flux it reaches, if the core reaches maximum flux, what happens after that? Already core is full. Saturation means what? This is full. Core is full of that capacity, and more than that, it cannot accommodate. Then it will demand very high magnetizing current after this. How it is? If you increase magnetizing current now, after saturation point, suppose if further magnetizing current increasing, then what happened? Flux already it is maximum. Now almost the flux will be constant. Very, very slight increment will be there, but not like previous linear. See, up to saturation point, linearly increasing. This is saturation. Okay, maximum flux. After that, saturation takes place. Now, up to the saturation point, linearly increasing. Observe, when current increase, flux also linearly increase. But after saturation, what is the increase in flux? Negligible, almost constant, but little slight increment will be there. Almost it is constant if you neglect the small increase. But for small increase in flux, see, this is maximum flux. Let this is some beyond the maximum. In order to increase little above the maximum flux, little flux, then how much current it will demand? Very high. So the magnetizing current required is very, very high. So like that, for small increase in flux, there is a large variation of current. Okay, remember this. That's why taken as flux density increasing means flux is increasing. So I mu also increases. And what happens to IW term? IW depends on what? Iron loss. For that, we have seen what happens to hysteresis loss and eddy current loss using these two equations. Okay. And then we have drawn the variation. I mu increase very much, but IW slightly increase. Then the sounds resultant of these two we got I naught. Then if you draw, what is the angle phi naught here? Increases. So whenever angle increase, the power factor decrease. Okay, that's why it is decreases. So similarly, second point I given, if both voltage and frequency reduce, if both voltage and frequency reduce such that V1 by F equal to constant, then what happened to no load power factor? So what is your answer? So directly also you can analyze, whenever V1 by F constant, what is Bm? Constant. So as flux density constant, what is the I mu? Same, no change in the I mu. It won't change. Now V1 by F constant means first case according to iron loss. So what happens in first case? IW we need, for that iron loss we have to check. Hysteresis loss proportional to frequency, eddy current loss proportional to frequency square. So as both are reducing, so hysteresis loss, frequency reduce, hysteresis loss reduce, frequency reduce, eddy current loss also reduce. So overall iron loss reduces. Then what is that corresponding IW term? Also reduce. The corresponding IW term also reduce. I mu remains same, IW decreases. So what happens to no load power factor? Okay, same as it is first point. Here also we have to analyze from phasor diagram. So what we do for this is, first we consider a reference diagram. Let it, this is V1. There is some magnetizing current and IW. This is our no load current. Okay, I naught. This is at some voltage and frequency V1 by F. Okay, this is the no load power factor angle phi naught. Now we have to apply the change given. So what is the change I given? Both reduce, voltage reduce, frequency also reduce. So I mu is same, no change in the I mu term. But what happens to IW? Just now we have seen. What happens? IW decreases. IW decreases. You can analyze from iron loss. If you have confusion again, go to iron loss. First case it is. So whenever frequency reducing, iron loss reduces. So I mu remains same, but IW decreases. So IW decrease. So new I mu is this same, and new IW is this. Now resultant we have to draw. Now this is same only, and if you take resultant, this is the resultant. Now what happens? The angle phi naught, I naught shifted little like this. Then the angle phi naught compared to this phi naught increases or not? Yes, phi naught increase. Then what is the no load power factor? Cos phi naught. Power factor means cos phi value you need to tell. So phi naught increases, cos phi naught decrease. So for the second point also, what is the answer? Power factor decreases. Okay. So hope most of you got this. Hmm. Okay. See, we both voltage and frequency reduce such that V1 by F equal to constant, like that we reduced. So don't confuse that V1 by F, V1 reduce, frequency reduce means flux density reduce. How we reduce? Suppose there is some voltage previously 250. Okay. Now voltage I reduced to 100 volts, and frequency also I will reduce to 25 hertz. Now what is the V by F ratio? Check. 200 by 50, 4. 100 by 25, 4. So is there any change in the density? Flux density, no change. Same only, no? So that's why I mu is same. Okay. Now clear, Sahu? Yes, but don't apply every time like this. Reactance changes or factor means this is not directly winding reactance. That is the core reactance, core parameters. R naught, X naught are the core parameters. Okay, don't consider that. See, here the problem is hmm, how IW decrease. So clearly a given now statement IW how it is decreasing. Maybe you, some of you may come late. Maybe you did not listen how IW decrease. Vaishnavi iron losses are constant loss. Constant loss, but it is depends on what voltage, no? But whenever voltage is reducing, iron loss will reduce or not? Yes, reduce. So that is the change we applied. So don't say that whatever the changes in transformer, iron loss is constant. Not constant. Iron loss depends on voltage. If voltage change, definitely iron loss will change. And copper loss depends on what? Current. If current changing, definitely copper loss will change. So don't say that constant loss means what? Every time it is constant. It is depends on voltage. If voltage constant, definitely iron loss constant. Okay, don't confuse. Sai Charan Reddy, clear now why IW decrease? So every time you should not be again becoming new, because already we have seen V1 by F equal to constant, case 1 with respect to iron loss. What is hysteresis loss equation? Proportional to frequency. What is eddy current loss equation? Proportional to frequency square. Now what we did here? Voltage and frequency reducing. So whenever frequency is reducing, hysteresis loss reduce, eddy current loss also reduce. So overall iron loss reduce. That's why IW reduce. Okay. Okay, right. These type of questions are important in every objective type of question. Mostly without calculator we can solve this type of question, theoretical question. No need of any numerical solving here. Okay, this model is important. Take care of this. Let's see the third test, short circuit test. Third one is short circuit test. Yes, rating of transformer depends on size also, because volt ampere, nothing but E1 I1 or E2 I2 we write. EMF in transformer and current in transformer, E1 I1, like this we write. Okay, and in that EMF equation proportional to, that is what is the EMF equation? 4.44 BAN. So in that, EMF is proportional to flux density and area of cross section. Size AN means what? Size of area will decide size of core. Then if size of core is increasing, definitely size of transformer also increase. So if area increases, the magnitude of EMF can increase. It's because it is proportional to that area of cross section only. So more cross sectional area, more EMF. And if EMF is increased, volt ampere also increase. Okay. Next, third one, short circuit test. Short circuit test. Simply we call SC test. Now, what are the objectives of this test? Objectives means purpose. Just like in OC test. Why we conduct OC test? To find iron loss of transformer. Second, to find no load branch parameters. So in order to draw the equivalent circuit, you need that parameters or resistance, reactance, R naught, X naught, all you require. So that parameters we are finding from test only. So previously we calculated R naught, X naught, no load branch parameters we call, or shunt branch parameters. Now in short circuit test, we will find series branch or load branch. What is there in load branch? R01, X01. So that we will calculate in this test. Okay. And one more is we have percentage resistance, percentage reactance, percentage impedance of transformer, or per unit resistance or reactance, anything you can call. So this is also we can find from this percentage values or per unit values we can find from short circuit test only. So these are the objectives of short circuit test. Write that objectives. First point. To find which loss we find here, copper loss or variable loss, because in this currents will flow in winding. But in OC test, is there current? Yes, that is no load current only on primary. Only on primary, very, very small. That's why copper loss we neglect there, but here only copper loss we will get. Now, right, to find copper loss or variable loss of transformer. Variable loss of transformer. Next, second objective. To find series or load branch parameters. Series or load branch parameters. What are that load branch parameters? In series with load, in circuit we have R01 and X01. These two we will calculate here. Okay, next, third. To find percentage resistance of transformer, percentage reactance, and percentage impedance of transformer. Percentage impedance of transformer. So this is main purpose of this short circuit test. Okay. Now, in the first objective, we are calculating copper loss. So if you want total copper loss of a transformer, what should be the current in the windings? Tell me, what should be the current in the windings? It is a small current or half of the current or rated current. So whatever transformer windings are designed to flow to carry some rated or full load currents, we call that much current you have to allow in short circuit test. Short circuit test. But if you directly short circuit now with the rated voltages, your transformers will damage or windings will burn directly. So you should not apply rated voltage in this case. So those who completed in your lab experiments also, you may remember this. In short circuit, we no need to apply rated voltage. Suppose rated voltage of transformer is 400 volts. Okay, 400 volts, any one side, primary side. Then you no need to apply 400 here. You need to apply just a small voltage. Approximately the range is 5 to 10%. Small voltage is enough because winding is dead short circuit now. With a dead short circuit, for small voltages also high currents will flow. That's why if you apply rated voltage, very high currents will flow, windings will burn. For that reason, we no need to apply rated voltages. A small voltage we apply. So that voltage percentage is important for examination. 5 to 10% of rated voltage is enough in short circuit test. Okay, and this test should conduct at rated current. Previously, OC test we conducted at what voltage? Rated voltage. Why? There we need to find mainly iron loss. So we know iron loss depends on voltage. So if you apply rated voltage, then only you will get total iron loss. But now in short circuit test, we are able to find copper loss. So if you want to find total copper loss, what should be the current in the windings? The current in the winding should be rated or full load currents we call. Okay, write that point. This test should conduct. This test should conduct at rated current by applying a small voltage, by applying a small or reduced voltage, by applying a small or reduced voltage, and that voltage percentage is 5 to 10 percentage of rated voltage, 5 to 10% of rated voltage. So we will see in the figure with example how much voltage we are applying and where we are conducting this test. So LV side, HV side, two sides we have now, and where we conducted previously OC test, LV side, with open circuit on HV side. And can you conduct test any side first? Yes. OC test or AC test, you can do any side first. Any side you can do. LV side also you can do, or HV side also you can do. But particularly OC test, we preferred to conduct on LV side. Means where we given supply there for OC, LV side we given supply, HV side we open circuit. Due to some advantages, okay, that advantages we have seen. Similarly for short circuit test, which side it is preferred to give supply? Which side it is preferred to give supply? High voltage or low voltage? Now here opposite to OC test, high voltage side we prefer to give supply, because we need to conduct the test at rated current. Tell me which side rated current is less? High voltage side currents will be less. Low voltage side current rating will be high. So as we need to conduct at rated current, it is preferred to conduct this test on high voltage side. And other side, what we have to do? Short circuit. LV winding we have to short circuit. Supply is given to high voltage side. Okay, in the figure you will see everything. So make a note of this note. This test is preferred. This test is preferred to conduct on HV side, by short circuit, on LV side. Since, what is the reason? Since the rated current is less. The rated current is less on HV side. Due to this reason, we are conducting HV side. Otherwise, if everything is available, high current measurement meter is required. Ammeter required here, mainly ammeter. If you do the test on LV side, high currents will flow. So that current you should be able to measure. That's it. If you are able to measure with high rating ammeter available, then you can do the test on LV side also. Any side, if you do the test, your losses will never change. That may be OC test, that may be short circuit test. Loss you will get same wherever you conduct the test. But due to some advantages only, we are conducting some particular side. That's it. Okay. Now draw the figure. Take the figure. Same as OC test, voltmeter, ammeter, wattmeter. For voltage, current, and power, 3 meters required here. Now, this test we prefer to conduct on which side? HV side. And LV side, we short circuit. Okay, LV winding, I am short circuit. Short circuit. This is LV. Now, HV side, we are conducting test. So the required meters we need to connect here. 1 wattmeter we need to connect. This is wattmeter. And 1 ammeter is required to measure current drawn by transformer, and 1 voltmeter to measure how much voltage you are applying. But which is important here, your observation while conducting short circuit test, Your eye contact on which meter here? Ammeter, because you need to consider rated current. That's why your eye contact must be on ammeter here. But previously in OC test, our contact must be, eye contact must be on voltmeter, because rated voltage you need to apply there. So this is auto transformer or variac auto transformer. Here we give supply first to the auto transformer, and the output of auto transformer is variable voltage. Whatever the voltage you want, you can give, apply, you can apply slowly. That's why we are giving from auto transformer every time. This is voltage under short circuit, current drawn by transformer under short circuit, and watt meter reading, power drawn by transformer under short circuit. And remember, the type of watt meter under short circuit test is HPF, high power factor. Only under OC or no load case, no low power factor we have. That's why what type of meter we choose there, we have to choose LPF meter. But short circuit, HPF, high power factor, because here the power factor is little greater than 0.5 will be there. Okay, for that HPF meter you need to take in the lab, and 1 voltmeter and 1 ammeter and watt meter reading. Okay, so we are giving supply to which side? HV side, and short circuit on which side? LV side. Okay, now considering the rated voltage of high voltage is 400 and this is 100 volts. For example, the rating of transformer is this 400 by 100 volt. Now let the rated current on LV side is 10 amperes, and rated current on HV side is 10 ampere. LV side is, let I2 equal to 40 ampere. Okay, volt ampere same on both the sides. Calculate 400 into 10 for 4000, 40 into 100 4000. Volt ampere VI rating is same in both sides, but voltages currents are different. If you conduct the test on high voltage, what is the rated current? You need to measure 10 amps. So small current. So what is the type capacity of ammeter required for us? Low range ammeter is enough. 10 amps measurement is enough. But if you do test on LV side with short circuit on HV side, then how much current you need to measure there? 40 amps you need to measure. Then what is the ammeter range required? 40. Okay, that is high range required. May or may not be available, but low range is easily available for us. No, that's why we prefer to conduct the test on high voltage side with short circuit on LV side. Okay. Now, before going to the procedure, we need to know about two currents here. Two important definitions we have. Write that. So again, we come back to figure. First, write this. A rated short circuit current. Rated short circuit current. IS. Rated short circuit current. So what is the meaning of this? Rated current. Rated current means full load current. How to find full load current? Already I given in previous cases. Suppose there is a transformer of 4 kVA, 400 by 100 volt rating. How to find rated current of primary and secondary? Directly from this rating itself. That is I1 equal to 4K by 400, 10 amperes. And what is the rated current on secondary side? LV side. Same kVA, 4K by 100. This will be 40 amperes. Okay, like this we need to find. That is rated current or full load current we call. Now, what is rated short circuit current is? It is the rated current flowing in the windings under short circuit condition. Under short circuit condition. So how much voltage we need to apply for this? Observe the figure. 400 volts is the rated voltage of HV side. As it is short circuit, is it required to apply 400? No, you should not apply 400 by mistake. By mistake, if you concentrate voltmeter reading in this test, your transformer will burn, because maybe if you keep in mind 400 is the rated voltage and you are applying continuously 400 by observing voltmeter only, your transformer will burn. So your concentration in short circuit test is on ammeter only. Ammeter only you should concentrate. Forget about voltmeter, wattmeter. So slowly increase the auto transformer voltages. That is, you should rotate the knob, auto transformer knob slowly by observing what? Ammeter. And how much this ammeter should read? This ammeter should show the rated current of HV winding, which is 10 amperes. Now you have to observe for 10. Slowly increase the voltage. Observe the ammeter. Once ammeter shows 10, then stop that voltage. Don't increase further. Then take the remaining two readings. So how much voltage we need to apply under this test? Not rated. We need to apply the voltage under this test is 5 to 10 percentage of rated voltage, approximately. So this is called reduced voltage. No need to apply rated because dead short circuit now it is. With a dead short circuit for low voltages also high currents will come because load is not connected, directly short circuit. Okay. Now write the definition. Voltmeter followed by ammeter or ammeter followed by voltmeter, anything you can place. This is not a matter here. Only in a measurement subject, the people will discuss voltmeter. If you place after ammeter, there is some loading error, like that. So these are all we are not considering. Okay, anywhere you can connect a voltmeter, ammeter. That is not a problem. Okay, so what is rated short circuit current? It is the rated current flowing in the winding under short circuit with how much voltage applying? Reduced voltage applying. Right. That. It is the rated current flowing in the winding. It is the rated current flowing in the winding. Flowing in the winding under short circuit. Under short circuit with reduced voltage is applied. With reduced voltage is applied. With reduced voltage is applied. So that is approximately how much we are applying? 5 to 10% of rated voltage. This much voltage we apply. Rated current flowing in the winding under short circuit with reduced voltage is applied. Okay. So ISC nothing but simply rated current of the winding. That's it. Next, we have one more important current that is called steady short circuit current. Steady short circuit current. Now you can guess easily what is this steady short circuit current. So under short circuit, how much voltage now you are applying? Reduced voltage. Just 5 to 10 percentage of that voltage you are applying in order to get rated current. Now, if you apply rated voltage, how much rated? 400 volts. Then how much current will flow here? Very, very high current will flow or not? Yes. That is called steady short circuit current. So what is steady short circuit current? It is the current flowing in the winding under short circuit by applying rated voltage. By applying rated voltage, that is called steady short circuit current. If this current flows in winding now, definitely windings will burn because very, very high current that is cannot be withstand by the copper winding, it will melt. So how voltage we are reducing? That's why we are placing auto transformer. So the people who are in second year, third year, this is the problem. So if people don't know, but practically how voltage is reducing, how voltage we are reducing means auto transformer is the purpose. Have you not seen auto transformer in the lab? Hmm. The purpose of auto transformer is to increase the voltage slowly or reduce the voltage. Variable voltage we can get from auto transformer. Okay. So where the definition of steady short circuit current. So what is this? It is the current flowing in the winding under short circuit when you apply rated voltage. That is very high current it is. Right. It is the current flowing in the winding. It is the current flowing in the winding under short circuit by applying rated voltage by applying rated voltage by applying rated voltage. So at which current we have to do the test? We need to conduct the test, or we should do the test at rated short circuit current, but not steady short circuit current. So if you want rated short circuit current, how much voltage you need to apply? Only this much, approximately 5 to 10% you will get. Okay, that much voltage we need to apply. Remember these two. So you may get questions either on rated short circuit current or steady short circuit current. So how to find that steady short circuit current and all we will see, and we will see one question also, previous engineering services question we have. So there I will show you how to find steady short circuit current. Okay. Amrit Sagar, you are asking how voltage is 5 to 10% of rated and still rated current flows. It should flow at 400 volts. So actually, if you apply 400 volts, what you have to connect to transformer? Load you have to connect. Loads, any loads. But what you are doing there in secondary, are you connecting any load? No. What we are doing, directly short circuit of the winding. Short circuit means what? Zero impedance or zero resistance. So for zero resistance, if there is a low voltage, also high current. Suppose, see, the voltage on secondary side is 100 volts, 100 volts divided by what is the resistance of the transformer. Secondary will have some resistance Z2 impedance, but load is not having any impedance. What is the load? That short circuit, zero, that is. Now this is 100 and impedance of transformer is generally very small, let some 1 ohm. Then what is the current flowing? 100 ampere. Let this is the rated current. This is what high current, but rated current is generally very small, like 10, 20 amps, 30 amps, like that will be there, but very high current is flowing now. But when you connect load will have some impedance here, like 2 ohms, 3 ohms, 4 ohms, 5 ohms, in this range. If load is having some impedance, what happens to this current now? 100 by 1 plus, let us take some 3 ohms, 3. Then what is the current? 25. So when there is a load, what is the current? 25. That is the rated current. But when there is no load, directly you short circuited, what happens? 100 amps is flowing, and that is very high current or not? Yes. Then if you want to reduce this voltage, reduce this current 100, what you have to do under short circuit? Reduce the voltage. Okay, clear? Why we are applying low voltages? So no need rated voltage for short circuit case. Only load case you need rated voltages, but under short circuit you no need rated voltage. Clear? Sirisha, what is the main purpose of conducting this test? Already objective we have seen, no? To find copper loss, some objectives. Secondary side, you no need to measure because that is short circuited winding. Only primary side we are conducting, that current only we measure. Okay. Wherever you give supply, there you will measure currents, voltages, power, everything there only you measures. So where we are giving supply from the figure, high voltage side. High voltage side we connected voltmeter, ammeter, wattmeter. That's why there only. Okay. So what is the procedure? Now see the procedure. So LV side shorted and HV side voltmeter, ammeter, wattmeter connected. Now let us apply voltage to transformer using auto transformer. Variant. Slowly let us increase the voltage from 0. Slowly increase the voltage. 0, 10 volts, 20 volts, 30 volts like that. At one of the particular voltage, this ammeter will show you the rated current of this HV winding. What is the rated current of HV winding? With our example, 10 amperes. Now once this ammeter shows 10 amperes, so stop there. Don't increase the voltage further because already rated current is we got. Okay, already we got rated current here. So take the remaining voltmeter reading, ammeter, wattmeter reading. Voltmeter reading and wattmeter reading. Only single reading. Just like OC test, single reading only we take. Okay. So write the procedure in just 2-3 steps. Procedure. Procedure. Right. Apply voltage. Apply voltage to the HV winding. To the HV winding. To the HV winding using an auto transformer. Using an auto transformer. Using an auto transformer by observing a meter. By observing a meter up to it reads rated current of HV winding. Rated current of HV winding with short circuit on LV. With a short circuit on LV. Then take the readings of voltmeter and wattmeter. That's it. Okay. So read the procedure one more time. Pawan, is the video coming to you now? Check. Maybe from your side it is problem. Vishnu, how do manufacturer determines rated voltage and rated current? So I will tell all these details in Sampner's test. How they will decide the volt ampere rating of transformers. And Stravia, based on the resistance, we never decide current rating. Based on resistance, based on volt ampere rating, we will say that this is our rated current. Volt ampere we have now, kVA, volt ampere rating. Based on that, we will find the rated current of primary, secondary, and based on the current, you need to connect the load, and you should not connect the load resistance generally very high, 5 ohms, 10 ohms, 20 ohms like that. It never be less than 1 ohm. Only transformer winding will have less than 1 ohm, but not loads. Okay, don't think with respect to resistance point of view current. So I will tell all these details, so because people will confuse like this only. That is, suppose there is a transformer. You don't know anything about the transformer. You are getting some supply. That's it. Now, can you connect whatever the load you want to the transformer? Suppose you have very huge load, then can you connect to the transformer? No, you should not connect. You have to take care that how much load we can connect on the transformer. Same reason, no? Suppose if you take to your home, in your home, you are taking supply, single phase supply to your home purpose. Now they are giving single phase supply. They have some rating like 1 kilowatt is taken or 2 kilowatt is load is taken. How much load you are taking? So on the electricity bill, it will be there 1 kilowatt or 2 kilowatt or 3 kilowatt. How much load you are consuming? That you have to mention there. But that is not exact. Approximately, we will take that load. Okay, because why we need to why they want the how much load you are want who are connecting is based on that they will install the transformer there. There is a transformer, whatever the load you want to connect is you should not connect because transformer will damage if it is overloaded. So based on the transformer rating we have to connect load, and you should not connect your own whatever the loads you want because transformer should not damage now. So for that reason, based on transformer rating only we will connect the loads every time. So I will tell clear details in Sampner's test how we decide the rating of transformers and all based on heat. Yes, overload means high currents. Short circuit also high current, right? Yes, with high current, short circuit wire will get melt. That's why we are not doing at high current, no? Where we are doing short circuit test at rated current only we are doing. That's why how much voltage we are applying. Small voltage only we are applying to protect that. Okay. Others, that is the why you are still not understanding because uh, conducting test on HV side. So why we are conducting test on HV side? Because where you need to conduct the test rated current, no? So rated current is less on which side? High voltage side or low voltage side? High voltage side current is less. So if you put ammeter on high voltage side, how much the current ammeter should read? 10 amperes. High voltage side rated current 10, we take an example, 10 amps it has to measure. Or if you conduct the test on LV side, what is the rated current on LV side according to our figure? How much it is? 40 amps. So if you place ammeter on LV side, now how much current it has to measure? 40 amps it has to measure. That is the rated current on LV side. So 40 amps means the ammeter required range is very high or not? Yes. So because of that, high rating meters may or may not be available readily, but low rating meters every time available for us. That's why we prefer to conduct the test on high voltage side because the current is less. Yes, steady short circuit current will damage the winding. That's why we should not do this. Dwarakesh, which test is best, OC or SC? The purpose is different, no? OC test is different for different purpose. So both we should conduct. We should not say that this is best or this is not best. OC is for iron loss. SC is for copper loss. Both we have to conduct definitely. Okay. Rated current is the full load current from the rating whatever you calculated. High current means what? That may be suppose 10 amps is the rated current. High current means that may be 50 amps or 60 amps or 70 amps based on the voltage you applied. So that high current should not flow because we need to protect the transformer. So that we should take care. We should not apply high currents in transformer. We should take care of that. Okay. Yes, rated current means full load current only. secondary winding also will not melt because you are applying low voltage on primary, secondary also low voltage. Secondary is not high voltage. When low voltage on primary, secondary voltage also low, then current is rated current only there. It is not high current. Voltmeters we connect in parallel only, not series. Okay, across any winding we connect voltmeters in parallel. So in measurements you will get all these details. Yes, the steady short circuit current you can call fault current. Very high current it is damaging. Yes, rated equal to full load, right? Ashwani, after auto transformer we have to connect ammeter first. So what I said, you can connect ammeter, you can connect voltmeter. These are all not a problem. Anywhere you can connect this. Okay, anywhere. Next, see, continue this. This is the procedure. What is the procedure? Apply voltage from auto transformer slowly by observing ammeter. So what current you need to observe in ammeter? Rated current. Which rated current? High voltage winding you are giving supply now. So what is the high voltage rated current? 10 amperes. So that 10 amps is getting or not, you should observe slowly by increasing. Once ammeter is showing 10, now stop that voltage, then take the remaining voltmeter reading and wattmeter reading. So single reading we take. One is ammeter reading ISC and voltmeter reading VSC and wattmeter reading WSC. That's it. ISC how much? 10 amps rated current. Then how much voltage you need to apply? 400 we don't get. So if you do this practical, approximately you will get in the range 30 volts or 25 volts, like that. Small voltage you will get approximately 5 to 10% of this. So approximately you will get let 32 volts and wattmeter reading some 60 watts. So this reading you will get from the test. Single reading only we take, that's it. And then we remove supply to transformer and then calculations we do. Now see the calculations. Calculations means our objectives. What are the objectives of short circuit test? This is to find the copper loss, to find series branch parameters, to find percentage resistance, reactance, impedance. Okay. Now see the first objective. First objective. The first objective is to find copper loss of transformer. To find copper loss. How to find copper loss? So if you observe in this test, you are giving some input to transformer, but are you connecting any load to transformer on secondary side? No, we are not connecting any load. Directly short circuit the winding itself. So the output is zero here. You are not connecting any output, only the winding itself shorted. And then whatever power is given, that is drawing by transformer, and who will measure that power drawn by transformer? Wattmeters will measure. Now what is that power drawn by transformer? Almost equal to losses in transformer. Whether it is no load test, that is OC test, or short circuit test, power drawn by transformer equal to losses, that is given by wattmeter. So write that point first. During this test, the power drawn by transformer, the power drawn by transformer is equal to losses, measured by wattmeter, Now what is the wattmeter reading? Measured by wattmeter. Wattmeter we taken as WSC. So this is equal to losses. What are the losses mainly? Iron, copper loss. But Here you will get total copper loss because rated current is flowing. No, yes, total copper loss you get. But the iron loss, whatever you will get in this test is very small iron loss. Why? Iron loss depends on what? Voltage rating. Voltage you applied. How much voltage you are applying in this test? Observe how much voltage you applied. 32 volts only you applied. But the actual voltage rating of high voltage winding, how much here? 400. So iron loss depends on voltage. If you apply 400, total iron loss you will get. But how much voltage you are applying? Very small, 30 volts you are applying approximately. So iron loss you will get is small iron loss. A small iron loss. In previous test, copper loss is negligible, small, because only no load current. But in this test, iron loss is negligible, small, because small voltage only we apply. So if you want, therefore, the exact copper loss of transformer from the wattmeter reading, remove that small iron loss. Remove the small iron loss. So you will get the total copper loss of transformer. Okay. And mostly in the labs, we do that. The copper loss is approximately equal to wattmeter reading itself, neglecting the small iron loss. Neglecting small iron loss. Neglecting small iron loss. Okay. Approximately the wattmeter, whatever will give, that is itself copper loss of transformer. So this is our first objective, to find copper loss. Copper loss calculated from readings only. Wattmeter reading and small iron loss you need to calculate. Or if you neglect this, directly wattmeter reading itself, iron copper loss of transformer. Next, second objective. What is the second objective? To find R01, X01. Load branch parameters we call. To find R01, X01. Deeper, how to take wattmeter reading? So directly wattmeters will show, no? Wattmeters will show some reading that is in the watts directly. So wattmeters will give a power directly in watts. So whatever it is showing, just take that reading. That is the power drawn by transformer. Okay. Now in this test, which circuit we need to use? Second approximate circuit. We have two approximate, first and second. First we have used already in OC previously. Now we have one more from second approximate circuit. Second approximate circuit. What is that? Removing no load branch completely there. R01, X01. And here actual load is there, but now in this test what we are doing? Short circuit now. So short circuit. So this is our second approximate circuit. The voltage applied under this is VSC, current is ISC, resistance R01, X01. This is short circuit. Load is shorted. Load is not connected. In place of that, directly just a small wire is connected. That is called short circuit. Now no load branch is neglected here because a small current it is compared to this current, negligible. Okay, we need to find R01, X01 values. Dinesh, current is 10, voltage is 32, power is 60. So these are all approximate readings just I taken to show you. That's it. Here we are not having any calculation, any experiment details, nothing. Just to show wattmeter will give some reading. That's it. To show that I taken 60. If you don't like how it is 60 means, you take some other reading also, 50 or 40 or 70 or anything. Just to show some reading, I taken some values. You don't compare these values. This is just for your understanding, I taken some reading. Okay. Yes, whatever power drawn by transformer, that is loss itself. Okay. So because of this reason, so you should have good practical details with you. So whatever you are doing in lab, you should have that details with you first. But we never concentrate anything in practicals. Every doubt will come here. So how can we show? So I'm not having any transformer experiment in front of me directly, and not possible also. So this is itself taking so much time to complete one subject. Then if you are doing practical and showing and completely means uh, only transformer you have to complete electrical machine again 4 parts. Then how much time it will take to complete entire syllabus? Okay. Watt meter active power only. Watt meters active power only. Watt meters will show active power drawn by transformer. Okay, this is the second approximate circuit. Now we have the voltmeter reading, we have ammeter reading with us. So if you apply KVL in this loop, apply KVL, then what is VSC equal to ISC into R01 plus JX01. Okay. Now some of these resistance and reactance commonly we call impedance. This is VSC equal to ISC into Z01. Commonly we call impedance of transformer, that is. Now from this equation, first we can find Z01 VSC by ISC. Okay. So first calculate impedance. Directly substituting voltmeter reading here, ammeter reading here. Direct substitution from your readings, and you will get impedance of transformer first. Okay, impedance you got. Next, from the wattmeter reading, whatever wattmeter reading is there, that is copper loss itself, no? Yes, the wattmeter reading itself copper loss. Now what is the equation for copper loss? I square R loss is called copper loss. So I square R, I means ISC here. Resistance is total resistance R01. Why R01? You are getting total loss, not only one side loss. Total loss you will get. Power drawn by total transformer. So I square R, ISC square R01. We call total resistance referred to primary it is. So from this equation, calculate R01 value. WSC is the wattmeter reading. ISC square is the current reading. All direct substitutions from readings. You will get R01 in ohms. Okay. So R01 you got. Already Z01 also we got. Then which one we have to find? X01 we have to find. Once you know these two, then X01 easily we can find. How? Z01 equal to R01 plus JX01 now. Then what is the magnitude of Z01? Square root R01 square plus X01 square. Then what is X01? Root over Z01 square minus R01 square. So X01 you can find using this equation. Okay. First find Z01 and then find R01, then X01 using the previous two. So R01, X01 we can find like this. Okay. Yes. We are considering second approximate circuit because no load current is negligible. Total loss is due to copper loss one. Okay, this is the procedure to find load branch parameters R01, X01. Clear all of this calculation? Everything from readings only we are proceeding. Everything from readings and then calculations. Next, third objective. These calculations are referred to HV side because Whatever voltmeter reading, ammeter reading, wattmeter reading, everything from HV side now. That's why all these readings with respect to HV side. Next, third objective. Third objective. What is the third one? Third one is what? To find percentage or percentage X, percentage impedance of transformer. Percentage impedance of transformer. So these three terms we need to calculate: percentage resistance, percentage reactance, percentage impedance of transformer. Already we know about percentage R, if you remember this. What is percentage R? Nothing but percentage copper loss. What is the formula for that? Full load copper loss by rating of transformer into 100 will give percentage copper loss, which is percentage R only. So first you can find directly percentage R. What is the formula for this? Full load copper loss divided by volt ampere rating into 100. And from the given or from our data readings, what is the full load copper loss means? The watt meter reading itself copper loss. That is itself full load copper loss here, divided by volt ampere rating. So you know volt ampere rating from the nameplate, it will be available. Substitute directly. So like this we find percentage of WSC, substitute here. That's it. Rating already we have from the nameplate, and percentage R you will get from this. Okay. Now we need to find percentage Z and percentage X. Yes. Yes, good. Now observe this. From previous equation only I'm taking this equation. VSC equal to ISC Z01. Same equation I'm writing again here. VSC equal to ISC into Z01. Okay. We need percentage impedance. Observe carefully. To this equation, I am multiplying both the sides, dividing both the sides with EMF E1. E1 means what? Rated voltage, 400 volts. So I'm dividing both sides, rated voltage, ISC Z01 by E1. Now tell me what is IZ by E means. IZ by E. Previously in 2 days back or 3 days back in classes we have seen IR is what? Voltage drop, resistance drop or voltage drop due to resistance, divided by voltage. What we call this is per unit resistance. Like per unit reactance also we have seen. Now we got per unit impedance. So what is this now? IZ by E. This is called per unit impedance of transformer. Per unit impedance. Then if you want percentage impedance, what it is? Per unit impedance equal to VSC by E1. Now percentage impedance equal to VSC by E1 into 100. So percentage Z also you will get. Voltmeter reading divided by E1. What is E1 means? The nameplate transformer voltages 400 volts by 100 volts. We take an example, no? So this is E1. This is E2. So VSC is primary side, whatever you got reading, voltmeter reading divided by that E1, give percentage Z. So whatever I'm writing equations, you have to substitute directly your readings here. Okay. Percentage R calculation, percentage Z calculation. Now percentage X. Once you know R and Z, then what is the formula? Root over percentage Z square minus R square. Root over percentage Z square minus percentage R square. So here you will get percentage X. Okay, clear now all this? Percentage R, percentage X, percentage Z calculations from short circuit test. Full load copper loss means the wattmeter reading. We are conducting test at full load only, no? That is full load current only. So copper loss, whatever you got from the wattmeter reading, that is full load copper loss only. That's why direct that wattmeter reading we are substituting. Now, what is the problem if you take reduced voltage? You are getting rated current, no? And Shilpa, it's per unit voltage drop. How it is per unit impedance? See, per unit resistance drop or per unit voltage drop. Voltage drop may be due to resistance or due to reactance or due to impedance. So per unit resistance drop means we write IR by E. Okay. This is the same thing you can also call simply per unit resistance. That's it. No need to call drop here again. Per unit resistance of transformer is this. Now what is per unit reactance of transformer? IX by E. Similarly, what is per unit impedance of transformer? IZ by E. Okay, no need to write every time per unit voltage drop due to impedance or per unit voltage drop due to resistance. This much no need to write. That indicates directly voltage drop only. Okay, that's why I taken it is a per unit impedance. Clear? Conventional examination, they will ask about only one objective, like explain the procedure to find percentage or percentage X percentage Z of transformer. Then you need to write about short circuit test procedure, and then these equations you have to write. That's it. And they don't ask completely their explain short circuit test. Any one objective they will ask in conventional examination. So there you have to write procedure and diagram neatly, and then these equations. Okay. Okay. Yes. No load loss means iron loss, and short circuit loss means copper loss. Yes. In OC test, why we use first approximate circuit, short circuit, second approximate? In OC test, load is removed. If you remove load, what is there? R naught X naught. That is we call first approximate previously. That's why we taken. So accordingly, it's very difficult for a faculty members here uh, to explain this type of doubts when compared to offline class. Very difficult. And you people may listen by sitting or by sleeping or by walking anyway, but we should sit at one place only for long time. Difficult for us. If you conduct, why, how conducting test on LV side and HV side gives same result, Aishwarya? How it is? Suppose how much wattmeter reading I taken? 60 watts. Okay, copper loss is 60 watts. Okay, internet problem. Yes, I am not visible. Just now I got visible. Okay. Okay, right. So whether you conduct the test on any site, LV side or HV side, you will get the same copper loss because resistance is different. No, if you conduct test on high voltage, we taken the current 10 amps, so 10 square into the resistance corresponding to primary side, that is HV side. If you transfer or if you do the test on LV side, no, your resistance will change. So I square R, you will get same value. Okay, anywhere you will get the same loss. What is the importance of per unit quantities? Per unit quantities. So clearly you will get about per unit quantities in the power system subject. But what is the main use of this per unit quantities is to make the calculation very easy. So here in per unit, you will deal with 0 0.1, 0 0.2, 0 0.51 like that. So that is small numericals, but not like 10 kVA, 100 kVA or 400 volts or 2000 volts. This much big numericals you don't get. In per unit system, the calculations will become easier compared to units. That is in voltages, currents, volts, amperes. Better than that, if you go to per unit, calculation will become easy. So for one transformer, you can do easily. But if you observe outside in distribution or transmission, do you have one transformer? No, there are hundreds of transformer. If you check in your street itself, beside one or two streets, you can see nearly 4 to 5 transformers, not single transformer. No, that depends on loads. If load is more number of transformers they should install. Okay, so for that reason, then we go per unit quantities, per unit values. Calculation becomes simple with that. This is our third objective, to find percentage or percentage X and percentage impedance of transformer. Okay, now before going to that small example question, I will give the how to find steady short circuit current. Okay, how to find rated short circuit current? Tell me, rated short circuit current, nothing but a rated current. How to find that? KVA by voltage rating, that will come directly. Now how to find rate steady short circuit current, and that is I said very high current, and that current we need to calculate. See how to find that. Right, side heading, steady short circuit current. Steady short circuit current. This is I'm indicating as ISSC, steady short circuit current. Okay, first, what is the rated short circuit current? Previously we calculated that from the readings. Rated short circuit current, this is we indicate as ISC. No, how to find that ISC? From previous equations also. See, from this equation, VSC equal to ISC Z01. ISC means rated current. How to find that? From this VSC by Z01. VSC, low voltage. We are applying low voltage divided by impedance of the transformer windings. This will give rated current. Okay. Now, if you want a steady short circuit current, what we need to apply? Rated voltage you need to apply. Steady short circuit current, that is ISSC equal to rated voltage you have to apply. What is the rated voltage? E1, primary voltage, whatever is given, that HV voltage, that is E1 divided by Z01. It will give steady short circuit current. And in most of the questions, they don't give impedance. These are in voltages in volts, impedance in ohms. Then you will get amperes. But in most of the numericals, you will see percentage voltages or percentage impedance. Then if it is given in percentage, now we have to convert this steady short circuit current also to per unit steady short circuit current or percentage steady short circuit current. So how to define this? Per unit steady short circuit current. Per unit steady short circuit current. What is the per unit definition? Per unit value is nothing but actual value, anything that is voltage, current, resistance, impedance, anything same. What is that actual value divided by base value? But both should be in same units. Voltage by voltage, current by current, resistance by resistance, or impedance by impedance, same should be there. Base value. Base values means always rated values in any system. That may mean power system calculation or in machines, anywhere base means what? Rated currents or rated voltages. Okay, directly you have to substitute. Actual means now whatever you are calculating. I am calculating steady now. So steady short circuit current by base. What is the base? Always rated current. So the per unit steady short circuit current, it is defined as per unit ISSC equal to steady short circuit current. Actual current is this divided by base current. What is the base? Means always rated. What is that rated current? ISC. ISC. ISC or I rated you can write, or IFL full load current. All are same only. Okay. Per unit steady short circuit current. It is the ratio of steady short circuit current by rated current. Okay. What is ISSC? This equation E1 by Z01. Let us substitute here. So moving to next page. So just a definition I written. Per unit steady short circuit current is the steady short circuit current by rated current. That is the base always. Rated current is the base. ISC means I rated. I rated. You can write I rated or ISC. ISC means rated current. Next. Therefore, per unit steady short circuit current equal to ISSC. What is ISSC from this equation? E1 by Z01. E1 by Z01 divided by ISC. Okay. E1 by Z01 divided by ISC. So this is E1 by Z01 into ISC. In place of ISSC, I written this equation E1 by Z01. That's it. Now, I will divide this E1 in the denominator of this ISC Z01 by E1. Same only, no? That is just that E1 I taken at the denominator. Same E1 by ISC Z01 I written like this. Okay, no change in this. Both are same. Both are same. Now check here. IZ. What is IZ? Impedance drop divided by voltage. Voltage by voltage. Now what is this term? This is per unit impedance of transformer or not? Yes. This is 1 by per unit impedance drop of transformer. 1 by per unit impedance. Therefore, per unit steady short circuit current is nothing but 1 by per unit impedance of transformer. Very, very important. Very, very important. Never forget this equation. So we will see one numerical also question so that you will understand how to solve these questions. But you should know this data first. Otherwise, you cannot solve that question. Okay. And one more point I need to tell here. Observe this. In the previous, this percentage R, observe percentage R or per unit impedance. This is per unit impedance in terms of voltage VSC by E1 we got. So if you observe carefully this equation, percentage Z, this equation, percentage impedance of transformer is nothing but the percentage of voltage required under short circuit only. No? VSC by E1. E1 means rated voltage. Suppose impedance is given 6%. Now what it means? VSC equal to 6% of E1 only. No? Understand? They given in the question impedance of transformer 6%. What it means? That is nothing but percentage of VSC you can consider or not? Yes. VSC equal to 6% of E1 means how much voltage you need to apply? 6% you need to apply. Whatever is there that high voltage, in that 6% you have to apply. So right here, percentage Z, it is nothing but it is nothing but it is nothing but the percentage of rated voltage, percentage of rated voltage required, percentage of rated voltage required under short circuit, rated voltage required under short circuit, under short circuit to flow rated current, to flow rated current, to flow rated current. Percentage impedance itself, the percentage voltage you need to apply. Okay. Okay, I will solve. Yes, ISSC very much greater than ISC. So why ISSC we are calculating? We know we should not do the test at steady short circuit current, which is very high, we said, and how much it is, that we should know now how much value it is. So that is we are calculating using this equation. Okay, per unit steady short circuit current, it is equal to 1 by per unit impedance of transformer. Okay, so if you see the question you will understand. Okay, if you see one question you will understand. Now the same question I am showing to you now. Observe. First, see this. See this question first. See this. See the question. A 1000 by 100 volt power transformer. 1000 volt by 100 volt power transformer has a short circuit voltage of VSC. That voltage they given 40%. Actually, practically it is never 40%. Numerical they can create anything, no? Okay, don't get that doubt again. So you said 5 to 10%, they given 40%. You should not get this type of doubts. 40%. Which one of the following statement is correct? So what is that 40% means? You need to apply 40% of that rated voltage. What is the where you conduct short circuit test always? If it is not mentioned also, you should consider short circuit test always on high voltage side only. Okay. First option is a voltage of 400 volt appear across short circuited secondary terminals. If you short circuit, what is the voltage there first? 0. Short circuited terminals, when you short, the voltage is what? 0 there. So this is wrong. First option is wrong. Second, a voltage of 16 volt appears across the short circuit. Across short circuit 0 only always. This is wrong. Next, third, when the secondary terminals are short circuited, the rated current flows at the primary side at a primary voltage of 400. So this is right or wrong? Primary means what? That high voltage only primary here, because there only we conduct test. 40% means what is the voltage? 1000 volts is the rated. What is the 40% of that? 400. So VSC is the 400. This much voltage we are applying. Then rated current will flow or not? Yes, rated current will flow. So this C looks right. Okay, then check one more. D also. Primary voltage drops to 400 volt. No, this is wrong. Primary voltage will not drop to total 400. Drop is always very small. So not 400 volts. Supply voltage is 400, but not voltage drop. So this is wrong. Option C is correct. Okay. So got it all of you? Check one more time the question and option. So for that reason, I said each and every point in your notes is important for engineering services. Okay, the procedure also important, and whatever we have seen that objectives, they are also important, each and every objective for engineering service. But for GATE, I can say not important everything. Only some particular topics are important for GATE examination. Okay, next one more question. Completed this. Now see this question. Read the question. Short circuit test is performed on a transformer with a certain impressed voltage. Means some voltage we are applying in a low voltage at a certain impressed voltage or reduced voltage at a rated frequency. Okay, initially short circuit test is performed at some voltage VSC. Okay, some voltage we given reduced voltage to get rated current at some frequency. This is initial. Now read the question from here. If the short circuit test is now performed with same magnitude of voltage, now same magnitude of voltage we applied, okay, VSC, but at a frequency higher than rated, previously F, now the frequency increases, then magnitude of current, previously when you apply VSC at F, we have some current ISC. Okay, we have some current ISC at that time. Now the question is, same test again conducted with same voltage, but frequency only increase. What happens to current and also power factor? Both they are asking. Power, current and power factor are dash. Increases, decreases, or both increases, or both decreases, or what happens? Try to guess this. Try to answer this one. Try to answer. Nominal means rated. Nominal means rated. Easy one, not difficult it is. Observe. Initially voltage applied VSC at frequency F. Then there is a current ISC. How to find current from short circuit test? VSC by Z01 only, no? VSC by Z01. Just now we have seen that equation. This will give current. Now VSC by Z01. Z01 means what? Root of R square plus X square. R01 square plus X01 square. This is current equation. Okay. Now voltage we are keeping same, no change in the magnitude, but what happens to frequency? Increased. So whenever frequency increase, which magnitude will change? Resistance or reactance? Resistance is what? Independent of frequency, but reactance, inductive reactance, equal to omega L, which is 2 pi f into L. So X is proportional to frequency. Okay, reactance of the winding proportional to frequency. Whenever frequency increase, what happens to reactance? Also increase. Now put that is here. Therefore ISC is VSC by root R01 square plus X01 square. Therefore, as reactance is increased due to frequency increase, what is the current? It will decrease. So magnitude of current, it will decrease. And what happens to power factor? We need to check. Tell me from the impedance triangle Z01, how can we write R01 plus JX01? How we draw the impedance triangle? This is a resistance component R01, this is reactance X01, and this is resultant impedance Z01. Root of R square plus X square. Z means root R square plus X square, perpendicular. These two are perpendicular. And this angle we call power factor angle phi. This is called power factor angle from the impedance triangle. Now, what is cos phi from this triangle cos phi, adjacent side by hypotenuse, R01 by Z01. Okay. Now, as the frequency is increased, what happens to impedance? Increases. Then what is the power factor? Decrease. Already current is decreased. Now power factor also decrease. So both current and power factor of transformer reduces. Okay. So which option it is? The magnitude of current, and power factor will both increase, in both decrease. So this is option D is correct. Okay. Current decreases, power factor also decreases. You cannot use phasor diagram here because that is no load phasor diagram, but this is load or short circuit case. No, directly you can use these relations cos phi, because what is the circuit under short circuit? R01 X01 short, only that small circuit. No, so with that directly you can utilize the equations. Phasor diagram we cannot draw for short circuit. Okay. How current decrease? Observe the equation. From equation, no, this is Z01. So everything I given in equation, again still you are not observing. VSC is what? VSC by Z0, that is ISC equal to VSC by Z01. When your frequency increase, reactance increase, so impedance increase, voltage remains same, that is given in the question. Then what happens? Current decrease. Okay. Clear it is. So like that they may give, if voltage is again constant, frequency decreases. Now here increase given and you may get decrease, then what happens? Current and power factor increases. Or if both voltage and frequency reduce such that V by F is constant, then what is the current? So this type of variations. Okay, take care of this. Like this you need to solve whatever the variation they given, apply these equations, you will get the answers. Next question. See this question. In this question you need to find a steady short circuit current. Steady short circuit current is dash. Read the question first. A 10 kVA 400 volts by 200 volt single phase transformer with 10% impedance. See this rating mostly in every questions you will get, like voltage rating, kVA rating, they will give in the question. Or if it is nameplate of transformer, that will be there on the nameplate. Okay, this data will be there everywhere. Voltage rating, power rating, that is volt ampere rating. And given here 10 kVA is the capacity of transformer, 400 volts by 200 volts. This is E1 by E2 given. And percentage impedance is 10 percentage with the 10% impedance. So percentage Z equal to 10%. Now it is drawing a steady short circuit current of dash. So try this question. We need to find steady short circuit current ISSC. Observe this steady short circuit current. In the options we have amperes. So because we have the equation per unit steady short circuit current, what is that? 1 by per unit impedance. But if you directly take, that will be wrong, because they are not asking in per unit, they are asking in amperes. Okay, so don't confuse, I will write clearly here. We have the relation per unit steady short circuit current is 1 by per unit impedance of transformer. So what is given per unit impedance? Percentage given 10%. So what is per unit impedance? Means 0.1 divided by 100.1 per unit it is. Now 1 by 0.1, then how much we will get? 1 by 0.1 means 0.1 is 1 by 10, so it is 10 per unit. So per unit steady short circuit current is 10 per unit. Suppose if they ask options in per unit, 10 you have to check. 10 per unit is the correct. but they are not asking in per unit, they are asking in amperes. So you have to convert this. How it is, what is the definition of per unit steady short circuit current? ISSC by ISC equal to 10. Actual value by base value. But we need actual is how much? So ISSC equal to 10 into ISC. What is ISC? This ISC is nothing but rated current or full load current. How to find rated current? Given rating here. Utilize this and find the rated current. From this, which rated current? Primary or secondary? Wherever high voltage winding, that may be primary side or secondary side given in the question. Here anyhow 400 is on primary. So that HV side current you have to calculate. So that is ISC equal to 10 into 10 cube divided by 400. How much it is? This is 25 amperes. Okay, this is rated current on HV side. Substitute that is here. 10 into the rated current 25. This is 250 amperes. Okay, steady short circuit current is 250. Now check here. What is the rated current of the transformer? 25. But if you conduct the same test for steady short circuit current, I said it will damage. Why? This is the reason. How much current is flowing? 250. 10 times of actual current. 10 times. 25 is the rated, its capacity. But current flowing at that time is 250. Definitely it will damage the transformer windings. Okay. Yes, right. 250 amperes. Now clear how to find steady short circuit current? If they give an impedance, from that impedance you can find per unit value and then it is converting to amperes. Okay, so take break for 15 to 20 minutes maximum, and after the break we will see the questions related to these both tests, OC test and SC test. Some more questions, and then we see finally Sumpner's test. So once the Sumpner's test is complete, total test will be completed, then we will start performance of transformer. So these are all in sequence. See, first we have seen construction. First we have seen construction part, and then we have seen operation of transformer, how to operate or what are the terms related in transformer we have seen, and then we have seen losses, and then we conducted next step to find performance. What is that performance? One is efficiency. Calculating. Do now. Yes, completed. Now you can sell the transformer. Performance. So with that, our single phase transformer topic will complete. So after that, we will see three phase transformer. Before that, we have to see the non-linear nature of BH curve. Why? What is the problem? So fifth ideal we left. Fifth ideal property. So that we will see after completion of performance parameters. Then we go to three phase, and once three phase is complete, and we'll see some special connections like Scott connection or open delta connection, delta zigzag star connection. These are all. And finally, parallel operation and auto transform. Okay, mostly up to this weekend it will take. Okay, take break. See the next question. See this question. Read the question first. See here, there is a transformer rating. What is the rating? 230 volt by 115 volt, 2 kVA single phase transformer it is. The following watt meters available in the laboratory. Okay, there are 4 meters, watt meters. We need to choose 2 meters. The watt meters used in open circuit test and short circuit test of transformer respectively. So we need to choose 2 meters. One is for OC test, other is for short circuit test. Now, which 2 meters you will take from this? Out of these 4 meters, you need to take 2. One is for OC, other is for SC. Which 2 watt meters? So what is the answer? Yes. Okay. Okay. W2 and W3. Yes. W2 and W3 it is. W2 and W3, right. W2 and W3. Options D is correct. Yes, most of you given right. W2 and W3. Because out of W1 and W2, 1 meter for OC. Because in OC test we use LPF watt meter, low power factor meter. So the LPF is there here. And out of these two, we need 1 meter for short circuit test. So in short circuit test, we use HPF watt meter, high power factor. Means HPF or UPF meter will call. HPF meter or UPF means unity power factor meter. Both are same. Now out of these two, one is for SC. Now here 250, 250. Same. Now we need to check regarding currents. And again in W3 and W4, 150, 150. So we need to check current. So current, with respect to these currents, we have to choose. Now OC test we conduct on LV side. Okay, OC test we conduct on LV side, low voltage side. we will give supply to low voltage side, 115 volt rated voltage. Now under OC or no load condition, the current drawn by transformer, how much? I naught. How much I naught it is? Very small, just approximately 5% of rated current, very small current. So to measure that small current, do you require 10 ampere or 5 amps is sufficient? Or which meter will give the accurate reading? 5 amps meter will give accurate reading, because 5 amps is scale elaborated, 0, 1, 1.5, 1, 2, 2.5, like that. 0 to 10 it is elaborated, 0 to 5. 5 means elaborated scale. 0 to 10 reading is very small. So first you calculate, if you want, with respect to given rating, what is the current on high voltage side? Current on high voltage side, 2 into 10 cube divided by 230. Rated currents I'm calculating first. Rated current 2000 by 230. This is 8.7 amperes, approximately 8.7. Okay, this is the rated current on HV side. Similarly, what is rated current on LV side? 2000 by 115. This will be double, 17.4 amperes. Okay, these are rated currents. Now on LV side, we are conducting OC test. Now LV side rated current is 17.4 amperes. Now what is the 5% of that? Approximately 5%. 0.05 into 17.4. How much it is? 0.87. So we need to measure in no load test or OC test only 0.87. So to measure only 0.87, 5 amps is enough or 10 amps is required? Or which meter will give the accurate reading? 5 amps meter will give accurate reading. That's why W2 is suitable for OC test. 10 amps also you can use, but problem is what? 10 amps means scale is 0 to 10. We need to measure very low value, that is very difficult in that. Accurately it is difficult to measure. That's why 5 amps is best to measure that small current. That's why W2 is for OC. Next, out of W3 and W4, we need to choose 1 meter for short circuit test. Now again current reading only we have to check. Now where we conduct short circuit test? High voltage side. High voltage side we conduct short circuit test. What is the rated current on high voltage? 8.7. This is the rated current. So we need to measure how much current? 8.7 amperes. So for that reason, in order to measure 8.7 amperes, what is the current or ammeter required? 5 amps is not sufficient. Definitely 10 amps is required, because 8.7 we need to measure. 10 amps meter is required for this. If you take 5 amps meter, it cannot show, because the range is 0 to 5 only for this. That's why W3 is required for short circuit test. So which two? W2, W3, option D is right. Clear? Yes. Clear all of you? How I naught is 5%? In previous classes I given in the no load operation, the no load current is approximately 5% of rated current. That's why 5% of that rated current I taken. Okay. Option D is right. Next question. See this question. In transformers, which of the following statements is valid? In an open circuit test, copper losses are obtained. In short circuit test, core losses are obtained. This is wrong because in OC test, what is the loss we are calculating? Core loss. And short circuit test, copper loss, but they given reverse. Second, in open circuit test, current is drawn at high power factor. In OC test, the current drawn is what? The current drawn is no load current. What is the power factor under no load condition? Very less, low power factor, but they given at high power factor. So this is wrong. Okay. Next, in a short circuit test, current is drawn at zero power factor. So in short circuit test, power factor is higher power factor, no, greater than 0.5 will be there mostly, but they given zero power factor. So this is wrong. In an open circuit test, current is drawn at low power factor. So this is right. Yes. Yes, option D. Okay. Next question. Next question. See this question. A 50 hertz single phase transformer draws a short circuit current of 30 amperes at 0.2 power factor lagging. Actually, under short circuit, power factor is greater than 0.5, but numerically is given like 0.2 power factor. Okay, whatever it is. When connected to 16 volt 50 hertz source, what will be the short circuit current and power factor when same transformer is energized or connected to 16 volt 25 hertz? So just now in the previous 2-3 questions previous, we have seen one question. By keeping voltage constant, frequency reduce under short circuit, what is the current and power factor? Same question with numerical they asked. Now, previously, what is the voltage initially? VSC equal to 16 volts at frequency 50 hertz. Okay. Then the short circuit current they given ISC1 equal to how much? 30 amps. Okay, initially. Now the question is voltage they are keeping same 16 only, but frequency how much now? 25 reduces. Frequency is 25. Then what is the current? Short circuit current is how much? And power factor is also how much? Cos phi s. Now first tell me generally, whenever frequency reduced, what is the current and power factor? In the previous question, there we have frequency increase, then current and power factor both decreases. But here frequency decreases from 50 to 25. Then what is the current and power factor? Increase. So both will increase. What is the current previously? 30. Now greater than 30. So all options are greater than 30 only. And power factor is previously 0.2. Now power factor also increase and all options are greater than 0.2 only. So we should solve this. Otherwise, if you know at least like this, no, if they given different option combination, if you know that you can directly put that based on given option. But here the options are given, all are having greater than only. That's why we should solve. We should solve this. Try this question first yourself. Try this question. So try to solve. Whether it is right or wrong, first try to approach the question. That is important. See, initially given the voltage under short circuit is VSC 16 volts, 50 hertz frequency. Then current is ISC1 equal to 30 amps and power factor also given cos phi sc 1 equal to 0.2. It is what before change in the frequency. Initially, this much data is there. Now, according to this data, you can find Z01 first. What is Z01? VSC by ISC. And what is that? 16 by 30. How much? 16 by 30. Calculate. This is 0.533 ohms. This is impedance of transformer. Okay. This is impedance. And from cos phi, we know that cos phi SC. So already I written previously. That's why I'm not writing again the complete equation. Directly I'm writing cos phi SC is what? R01 by Z01. Okay. R by Z. Cos phi equal to R by Z. So from here, R01, Z01 is there. Power factor also there. Resistance you can find from this. So R01 equal to Z01 0.533 into cos phi SC, that is 0.2. Calculate 0.107 ohms. Okay, this is resistance of winding, and resistance is there, impedance is there. Now you can find from this reactance X01, root of Z01 square minus R01 square. Calculate X01. Solve simultaneously, you have to solve 0.533 square minus 0.107 square. This is 0.522 ohms. This is reactance. So all these values are for this data. Initially it is. Initially these are the resistance, reactance, impedance. Now given the change is this. Voltage is same, frequency reduced to half, 25. So first take up to this. Yes, good. Taken. Now voltage remains same, frequency is half. VSC remains same, 16 volts, but the new frequency is 25 hertz. Frequency is half. Now we need to calculate what happens current, new current ISC2 and new power factor cos phi SC. Cos phi is the power factor. Why I'm writing SC? Because it is under short circuit. Cos phi SC. Second case 2. This is how much. So whatever frequency variation, resistance remains same or not? Yes. R01 resistance will not change. Whatever is there previously, same resistance 0.107. Okay. And new reactance. Reactance will change. Why? X proportional to frequency. If frequency is half, what is the reactance also? Half. So X01 new value is X01 old value by 2. Half of that. What is the X01 previously? 0.522. So this is 0.522 by 2. Calculate 0.522 by 2. 0.261 ohms. This is new reactance after frequency reduced to half. Okay. Now resistance is same, but reactance is changed. So impedance also will change. New impedance square root R01 square plus X01 new square. Substitute here and calculate. What is this? Root of 0.107 square plus 0.261 square. 0.282. This is new impedance. Now we have new impedance. Now you can find current. Therefore, new current ISC2. Voltage is same, VSC by new impedance. This is 16 by 0.282. Calculate this value. 56.74 amperes. And what is new power factor? Cos phi s c2. Same formula R01 by Z01, but new value it is. Calculate this. 0.107 divided by 0.28. This is 0.379. Okay. This is the power factor. New current, new power factor. Yes, right. So got it all of you same current and power factor. So answer is 56.7 and 0.379. So this is the answer. Option A is right. Okay. So theoretically, we can say both increase with respect to equation point of view. But if you want to solve exactly, procedure is this. Okay, clear? So got it all of you. So first we calculated resistance reactance in first case. And then after change in the frequency, again we calculated accordingly. When frequency change, reactance only change. No change in the resistance. Okay, next question. Completed? See this question. This is previous ES engineering services question, objective type. Why I written x by 2? Because it is proportional to frequency, no, from here. What is the frequency? Previous frequency F1 is 50. Now what is frequency? 25. So whenever frequency reduced by half, x also reduced to half. That's why I taken directly by 2. Okay, Mamata? 100%. Ankur, at what percentage of rated current short circuit test is done? What percentage means? What percentage means? We are doing at rated current only, no? That is 100% rated current. See the question. Read the question carefully. The most important model and most confusing model also to you. This is previous ESC question. Without calculator also you can solve this. Without calculator you can solve. But try to understand the question. So if you cannot understand, you cannot solve. Definitely it is. Question is very easy, but only the thing is you should understand what given, what they are asking. See, there is a 1 kVA transformer and rating 200 by 100. Single phase transformer gave following test result on 50 hertz. So their OC test is conducted on LV side. What is the LV side rated voltage? 100. So 100 they given. And whatever this 20 watts is there, what is this 20 watts? Equal to iron loss only, no? Because in OC test, whatever loss is there, that is iron loss. Neglecting that small copper, that is itself iron loss. Short circuit test, HV side only. And this 25 watts is what? Copper loss. This is copper loss. Now given in the question, assume that no load loss components are equally divided. What are the no load loss components? No load loss means iron loss. And what is the components of that iron loss? Two losses, hysteresis and eddy current. So they are equally divided, means this is total 20 now. In that, hysteresis loss is 10 watts, eddy current loss is 10 watts. Okay, up to here it is clear. Now observe from here. The above tests were then conducted on same transformer at 40 hertz. Now what happened? Frequency reduced. And now also observe carefully. Frequency reduced. Previously 50, now 40 hertz. Same test again conducted. But if you observe carefully, OC test is conducted on high voltage side, not on LV side. They are changing, that is also. OC test is on HV side and short circuit test is on LV side. Short circuit test is on LV side. Now we need to find what is the reading corresponding W1, W2. Very important model. So try to read the question one more time and try to understand. So there is a small point. If you understand that enough, you will get the answer. Yes. Yes, sir. Tarun Kumar, right. Pratyush also right. Yes. Yes. Good. V by F ratio constant here. That you need to understand to solve that iron loss. Yes, good. Most of you are all good. Understand. One point you should remember, that is if you conduct the test on LV side or HV side, any test, losses remain same or not? Yes. Wherever you conduct, losses will never change. Same loss you will get. So what we have to do here is, previously they given OC on LV side, SC test on HV side. Okay. SC test on HV side. Now they are asking OC test on HV side, SC test on LV side. So what I can do here is, observe. I will change at 50 hertz case this OC test and SC test. Observe carefully. Now I am converting at 50 hertz OC test on HV side. Actually they given LV, but I am changing it is to HV. Anywhere you conduct, loss remains same. Okay. So when they conduct LV side, what is the rated voltage on LV? 100 volts. So 100 only they given. So if you conduct the same OC test on high voltage side, how much voltage you need to apply? 200 volt you need to apply. So for 200 volt, what is the iron loss you will get? Same iron loss, 20 only. So 20 only you will get. So iron loss is 20. No change, 20 watts. Now, short circuit test, they given on HV side. They given on HV side. First calculate what are the rated currents on HV side and LV side from this data. from the given rating, find what is the rated current on high voltage side. 1k 1000 volt ampere by 200, how much it is? 5 ampere. And LV side, LV side, what is the rated current on LV side? Calculate, this is also same, 1 kVA by 100, 1000 by 100, this is equal to 10 amperes. Rated current we calculated first. Now they given HV side first here, 5 amps they given. So rated current, what is the rated current on HV? 5, we got 5 only. So they also given 5. So if you conduct the test on high voltage side, what is the rated current? 5 ampere, and copper loss you got 25 watts. Now if the same test is conducted on LV side, if the same test is conducted on LV side, then what is the rated current there? Whatever you get, 10, so 10 amperes. Then what is the copper loss you will get? Same or not? Yes, wherever you do the test, same loss you will get. So same 25, copper loss is 25 watts. Okay, this is at 50 hertz. Now they are asking question at 40 hertz. When they conduct the test again at 40, they are asking OC side, OC test on HV side, they applied 160 volt. What is the W1 reading? And short circuit test they conducted LV side, and for 5 ampere they are asking what is W2. Okay, now very easy, it is simple. You just refer this 50 hertz and 40 hertz, refer that, easily you will get. First I am going to short first I am going to short circuit test, because that loss directly we can find. Observe here, both LV only, this is LV, this is also LV, so directly we can compare. See, for 10 ampere copper loss is 25. For 5 ampere, tell what is the copper loss? Half of the current, no? So 10 amps is the full load, copper loss is 25. For 5 amps, 5 means half of that. What is the half full load copper loss? So previously I given one equation, full load copper loss is 25. Half full load copper loss, x square into full load copper loss. X means 1 by 2, 1 by 4. So 1 by 4 into full load copper loss 25. This is 6.25 watts. So this is the copper loss, and W2 reading is this much, 6.25. The W2 means copper loss, 6.25 watts. Now only option A and option D is having 6.25 W2. So you need to check iron loss W1 reading also. First of all, this is clear for everyone. Copper loss calculation. For 10 ampere, this is the copper loss. Now they are asking here for 5 ampere, what will be the copper loss? 6.25. Okay, any doubt? This is clear, no? Copper loss calculation clear, everyone? Okay, right. Next, we have to find iron loss. W1 reading we need to calculate. Iron loss we need to calculate. See, they given initially here iron loss. What is the voltage? High voltage side. OC high voltage side, OC high voltage side. What is the voltage? High voltage side rated voltage is 200. This is 200. So I will write regarding iron loss separately here. To find iron loss, we are writing separately. See, initially they given at 200 volt 50 hertz. The iron loss is they given 20 watts. In that equally divided now, WH1 is 10 watts, WE1 is 10 watts. Now what they are asking at 160 volt 40 hertz they are asking. That is only question. See, they are asking HV side only 160 volt. Same side we have to calculate. Previously HV side we converted. Now they are also asking HV. And this is 50, this is 40. And what is the voltage they are giving now? 160 volts. That's why 160 40. What is the iron loss? That is the question. Which case it is first check? 200 by 50, 4. 160 by 40, 4. Okay, 160 by 40. Now case 1, In case 1, what is hysteresis loss proportional to frequency? Eddy current loss proportional to frequency square. Never ever forget this iron loss equations. It never leave you. In many numericals, the combination will come. In efficiency calculation, OC test, AC test again will come. There, if it is required to find iron loss, again you need to find. So never forget iron loss equation, because with this iron loss, definitely in your pocket either 1 mark or 2 marks are there every time, every examination. Then why should you forget this? Never forget. If V by F is same, first case, hysteresis loss proportional to frequency, eddy current loss proportional to frequency square. Okay, now use these equations. WH2 by WH1, F2 by F1. This is F1, this is F2. Okay, this is WH1. Total iron loss is what? Sum of the two losses. Calculate these two individually and substitute here. WH2 equal to WH1 is 10, new frequency 40, previously 50. And this is how much? 8 watts. Okay, 8 watts it is. Similarly, WE2 by WE1 equal to F2 square by F1 square. Now WE2 equal to, what is WE1 here? 10 watts. F2 square means 40 by 50 whole square. Then solve this, you will get 6.4 watts. So add these two, 8 plus 6.4, 14.4 watts. So this is the watt meter reading. Our iron loss is that much. So what is W1 in the given question? 14.4 watts is the iron loss. Okay. W1 is 14.4. So W1 14.4, W2 6.25. So option D is right. See, every question easy only. The only thing, the concept behind that question, you should know very well. That's it. And if you know the concept, you will understand the question first. Otherwise, if you don't know concept, what is OC test or AC test, where we do this, why we do this, if you don't know that information, then you will lose. You know, if you know very well, easily you can understand. Then if you practice some number of questions, easily you can solve any type of question. How WH1, WE1 are same? Because in the question I given already here, they given, no, it is assumed that no load loss components are equally divided. That's why the 20 I taken 10 10 equally divided. Okay, Pawan. Sivaram Krishna, you are which batch? Genco batch. Okay, one more Sivaram Krishna is there in Genco. Which one? Why did we take 25 by 4 in copper loss? Because yes. Hmm. I given previously one formula in losses. If you know full load copper loss, what is the copper loss at any fraction x full load? Fraction x is fraction 1 by 2, 3 by 4, or 70%, 80%. X square into full load copper loss. So this formula I used. X is half, no, it is 10 means full load, 5 means half. So 1 by 2 whole square, 1 by 4. Full load copper loss is 25. Okay. Okay. Next question. simple question, two questions, and then we go to next test, Sumner's test. See, at which condition of the transformer the equivalent circuit will be as shown in below figure. So where we use this circuit? Short circuit test. That's why I said each and everything important in engineering service. Every point in your book is important. So this is what load parameter now, or short series parameters, R01, X01 it is. This is R01, X01. Under short circuit, we use this. Okay. Next, same. This is when we use open circuit. Under open circuit, we have no load parameters, R not X not. This is under open circuit condition. Okay. With this, we complete the short circuit test, OC test. The last test is Sumner's test. Let's see that. Fourth one, Sumner's test. Sumner's test. This is also called heat run test. Heat run test, also called temperature rise test. Temperature rise test, and also in labs we call back-to-back test. Okay, these are the names for Sumner's test. So a small important point, this test not important for GATE, not important for GATE, and required in engineering services, but less chance to ask question theoretically, because no numerical question from this you will get. If you get any question, theoretical only, and about that Sumner's test you should know very well to answer that questions. Compared to written test, this test is important for interviews. In interview stages, this is very, very important. So many times, so many students face this topic, this test in their interviews. So they are asking what is the Sumner's test, and explain what is the importance of that, and why we conduct that test, and why the names are heat run, or why the names are temperature rise, why it is. So these type of questions they are asking. For interview point of view, this is very, very important. Yes, any frequency. Any frequency means they are asking directly current now in the previous question, 10 amps, 5 amps. So 10 current they are directly asking. So I square R, it doesn't depends on frequency. I they given, R will never depend on frequency. That's why directly you can use that formula. Okay. Now see here. Why the rating of transformer is given in volt ampere, and how we will decide the rating of transformers in the manufacturing stage. How we will decide rating? This is 10 kVA or 20 kVA or 100 kVA. How we are deciding rating of transformer, and everything I will show you here. Observe. This test mainly we use to find temperature rise of transformer. That is the main purpose of test, to find temperature rise of transformer. Temperature rise of transformer we can find in this test. Why not in previous test? Yes, we cannot find in previous test because OC test. When you conduct OC test, which loss is taking place? Iron loss. Is there copper loss? No, very small copper loss, that is negligible, no load copper loss. And while conducting short circuit test, which loss mainly taking place? Copper loss. And is there iron loss? Yes, but very, very small, because small voltage we are applying now, that is negligible. So in individual OC and SC test, you cannot find temperature rise of transformer. First of all, what is temperature rise? Heat from the transformer. So whatever losses we are getting, all losses is in the form of heat in the transformer. Iron loss, core heated up. Copper loss, winding heated up. Then overall temperature will rise. So in OC, which part of transformer is heating? Core only heating. In short circuit test, which part of transformer is heating? Winding, copper winding is heating up, but not both at a time. That's why it is not possible to find temperature rise or maximum heat of transformer in OC and AC test. But in Sumner's test, both the losses, iron loss and copper loss, both will take place simultaneously. Both. That's why we can able to find how much heat is developing in transformer. How much heat? So tell me one question. There is a transformer. There is one transformer in your street, and on the transformer, same load is connected for 10 hours. There is some load is connected to transformer, and some heat is produced. Let the heat generated in the transformer is 60 degrees centigrade in the transformer. Now same transformer operated for 24 hours for same load. After 24 hours, what will be? This is after 10 hours. And after 24 hours, what is the heat in transformer? Tell me. Is it same or increase or decrease? For 10 hours of operation, the heat in the transformer after 10 hours, 60 degrees, we measured. And same transformer, same load connected. Then after 24 hours, what is the heat generated? Generally, we think increase. Okay. Okay. Most of you saying increase and some of you same. Here the answer is 60 degrees only, almost 60 degrees only. Now same transformer, again same load is there. Again after 2 days, till same load is connected. Then what will be the heat in transformer? Almost same will be there. Same load is, I am saying, same load is there. Whatever load is connected, same load it connected to transformer continuously. 10 hours, heat is 60 or temperature is 60. After 24 hours, temperature 60. After 2 days, temperature is 60. But some people will think that temperature continuously increase. If you assume like this, every transformer will burn or not? Or in your street, there is a transformer. It will burn or not? 24/7, it is giving supply to you. It will burn or not? But it won't burn, because for every device, not only that, you take in your home ceiling fans also. Ceiling fan. That fan almost 24 hours will be operating, no? Mostly in summer duration, 24 hours it will be under running condition. Then if you operate 24 hours continuously, 2 days, 3 days, 4 days, the heat should continuously increase. Then that fan should burn. Is it happening? No. For years, 2 years, 3 years, 4 years, they are working continuously. So for every device, the temperature will go up to some maximum level and then saturate or fixed. Further temperatures will not increase for same load when you connect. Okay. Based on the maximum temperature rise. Based on the maximum temperature rise, we will decide what is the capacity of transformer. Now I will give one example also how we decide. Based on that only we decide rating of transformer. Now what is your duty? So if you should know about the transformer rating, this much it can supply. Then what you have to do? You should connect a load up to that capacity only. Otherwise transformer will overload. It will get overheated. Load increase means current increase, copper loss increases, heat increases. If it is beyond the limit of the transformer, windings will burn. So I will tell you now one small example how we decide kVA rating of transformer and why we are taking only volt ampere rating. Why not kilowatts, or why not reactive power kVA? Why we are not considering? See, once a transformer is constructed, no, once a transformer is constructed, voltage rating you can find by voltage ratio test. You give some voltage rating and you get some voltage rating on secondary side, measure with voltmeters, and then you will get the voltage rating. For example, 400 volts by 200 volt means when you give an input of 400 primary side, secondary side you are getting 200 volts. That is, you can measure by voltmeter. Okay, voltage rating you will get directly. Okay, voltage rating you will get, but kVA rating, this is you should not give directly. So you designed one transformer, voltage rating you given, and kVA rating, can you give my transformer will supply 20 or my transformer will supply 10? Can I give like this? No, you should perform some test, then only you can able to give that rating. How that rating is? Now I am considering this is my secondary voltage 200. Okay, secondary voltage is 200 volts. Voltage fixed, voltage never change. Voltage rating fixed in transformer, it never change. But I don't know what is the current rating to be connected, or what volt ampere it can supply full load. I don't know that. Now what I will do is, I will take a load, I will take a load of rating 10 amperes first. I will take a load of 10 ampere. Voltage is fixed one. Now I will take a load of 10 ampere. Some 10 amps load I will connect. Now what is the, connect a load of 10 amperes and check for maximum temperature rise, because once you connected load, transformer will not heat at a time. Slowly it will heat and then it will reach some maximum temperature after some duration, maybe that is 1 hour or 2 hour or 3 hour. So you need to wait up to maximum temperature rise you will get. Suppose for 10 amps load, I'm getting a maximum temperature from transformer is 50 degrees centigrade. Maximum 50, further it is not increasing. That is the maximum temperature rise. For which load? 10 amps load. Now what I will do is, I will increase the load because 50 degrees only I got. But according to our Indian standards, the maximum allowable temperature rise of transformers, not only transformer, for every machine is 85 degrees centigrade. This is maximum allowable temperature level. Safety of operation. Up to this temperature, no problem to transformer. Beyond that, if heat occurs, there will be a damage to transformers. Okay, this is keep in mind. For 10 amps load, I got only 50 degrees centigrade. So very less it is. Because in one of the interview, they asked, a transformer is operating under full load condition at its capacity. What is the approximate temperature of the transformer? They asked, what is the approximate temperature of transformer? That student said some 40 to 50 degrees centigrade, but that is wrong. They said 40 to 50 degrees centigrade, but that is wrong. Why it is wrong? First of all, they don't know practically what is the temperature. Then how can he tell? But they are asked. You should know that. Why? Because on the nameplate of transformer, everything will be there on the nameplate. So this nameplate I will show you in three-phase transformers, not right now. So there you will understand all this. But meanwhile, remember on the nameplate, temperatures also will be there. Maximum temperatures of this transformer. So they asked temperature is how much? He said 40 to 50, but that is wrong, because the temperature will be mostly in the range 70 to 75 degrees centigrade at full load operations. Remember, at full load operation, this much temperature will be there in transformers, because this is our general common sense. Like what is the outside temperature normal in summer period? Around 40 to 45, no? In summer 40 to 45 degrees centigrade will be there outside. And in transformer, what is the temperature? Definitely more than that. Why? Internal heat is generated, outside heat is there, and definitely it is more than 50 degrees centigrade. So that, like that, at least we have to give some answer, not 40 to 50 at all. Okay, now observe. So I have voltage rating 200, and step by step I will change the load. 10 amps I got 50 degree. Now I will increase the load, 20 amperes load I will connect, and again I will check for some time, for 1 hour or 2 hours. up to maximum temperature rises in transformer. Now the maximum temperature rises to 65 degrees centigrade. Still it is less only because up to 85 we can go, but we don't go up to 85, 75, 70 degrees we go mostly. 20 it is 65. Still no problem. I will increase some more load. I will check now again for 25 amperes. Now this time I got, for example, 70 degrees centigrade. Okay, this is enough for me. This is enough. So I will prefer my transformer to operate safely up to 70 only. I don't prefer more than that. Now 70 degrees I reached. Therefore, I will fix that this is the full load current of this transformer. Now already voltage rating is there, secondary. Now multiply this 25 here, multiply. Then what is the kVA? Therefore, volt kVA equal to 200 into 25. How much it is? 5 kVA, 5000 volt ampere or 5 kVA. This is the rating of transformer. Now I will print this rating on the nameplate. Now what that user will do? He will observe that 5 kVA. Means what? He will connect load accordingly. Up to that 5 kVA, he will calculate current. 25 amps we got, no? Now he will connect the load maximum up to 25 amps it is drawing. Not more than that. Transformer doesn't know anything. Suppose there is a transformer. There is a transformer primary, secondary. Okay, there is some voltage on primary and load is connected. When you connect a load, suppose you connected a load. Now transformer will supply whatever transformer wants, or load will consume whatever it requires. Tell me this point first. You connected a load to a transformer. Now transformer will supply whatever transformer wants, or load will consume whatever it requires. Which one is right? First or second? Load will consume or transformer will supply? Yes, load will consume. Okay, enough. Load will consume whatever it requires. Transformer is a innocent device. Nothing, it doesn't know anything. If you connect whatever the load, it will supply. It will supply continuously. If you connect very high load, it will supply, but it doesn't know anything. No, whenever it is overloaded, it will damage. So like that, whatever the load we are connecting, it will supply. So our duty is what? We have to connect the loads to the transformer based on its capacity. Okay, to protect the transformers, because they doesn't know anything. They will supply whatever you connect. So like this, we decide rating. So this heat is generated due to what? Losses in transformer. What are that losses? Iron and copper. So iron loss depends on what? Finally, voltage. Whatever the voltage you design, based on that iron loss, and whatever the current you take in finally, based on that copper loss. And due to that, always we give the rating volt ampere. Now clear? Now rating of transformer is decided based on what? Temperature of transformer. Temperature rise, maximum temperature rise. Now, when temperature will rise in transformer? When both losses are taking place. Now, in which test that is possible? Sumner's test. That's why this test we also call temperature rise test. Clear? So clear all of you now? What is the importance of the Sumner's test? Okay. Now, this Sumner's test invented by the scientist, name itself Sumner's. That's why we call Sumner's test, or heat run. Heat run. Why we are running the test? To produce heat. That's why heat run test. Temperature rise test. Okay. So this test required two identical transformers. That is the main thing in this. This test required two identical transformers. Okay, and see the connection for this, how we connect. And both OC test and SC test simultaneously takes place, not at a time. That is important observation in this. Simultaneously. How it is, I will show you. So first write one point. This test requires two identical transformers. Two identical transformers. Okay, so take the figure. See, power factor they don't consider in the manufacturing side. They don't consider about power factor. What is it is going to operate. So is the manufacturer no? This transformer is now going to operate for lagging power factor or UPF. No, that's why power factor they never consider in transformer. Only voltage current. That's it. Power factor they don't consider. Yes, 70 to 75 practically we prefer. Practically 70 to 75 degrees. Vishnu, where will we measure temperature? See, temperature means we have sensors now. Sensors. We will place just beside the transformer, that core and winding, beside the, not near core or near winding like this, near the transformer. So there they will measure, or surrounding they will measure complete temperature. Wherever they get maximum, they will consider that. Okay. How we decide 400 volts is rated on HV side? On the nameplate, it voltage rating is there, no? Then what is the problem? How can we decide this? On the nameplate, whatever rating is there, that is itself rated voltage. So as a user, that is we have to use directly. We are not manufacturer na, here. Whatever on the nameplate we have, same voltage we will utilize. Okay. Okay. Take the figure. Same as it is OC test and AC test, we have to connect this two transformers. See how we connect. The primaries of two transformers connected in parallel. This is one transformer, primary, secondary. First take the figure. Take the figure first quickly. So there are two transformers here. Both are identical. So this is one transformer, primary E1, E2, primary secondary of one transformer, and this is primary secondary of other transformer. Okay. First complete the figure. Yes, if the load increases beyond the rating. So based on KVA rating, we calculate current. Suppose rated current 25. No, if you connect a load of 30 amps, then temperature will increase or not? For 25, 70 degrees. Then for 30 amps, definitely temperature increase because loss increases, no copper loss. Then if it is 75, it may damage. Or if you connect 50 amperes, then it will be beyond 85 degrees centigrade, then your transformer winding may damage first. So at the higher temperatures, which one will damage in transformer first? Windings will damage. Core is strong one, but winding is what copper wire will melt after some particular temperature. That's why we should not connect the load above its capacity. Okay. Yes, definitely in summer, transformer temperatures will be beyond, sometimes beyond its limit, because loads connected also very high on transformers in the daytime also due to ACs we are switching on. So load temperatures very high, and in outside temperature is very high. So overall temperature may cross, but any due to that reason only 85 up to 85 no problem. That's why what is the range we are fixing at the design state? 70 only. So if summertime temperature increase or load is little increase also, it won't cross 85. But sometimes if it cross 85, then the winding sometime will get damaged. Due to that, some internal fault occurs and supply is power cutoff will be there from transformer. It will happen in summertime only. Identical transformers means what? Same voltage rating. Two transformers, same 400 by 200, 400 by 200, and same power rating, 10 kVA, 10 kVA. So that is identical. Transformers will not burst. So that is the noise of breakers. So isolators will be there. Whenever any fault occur, that isolator sound that is. Common breakdown is what? Fuse problems. Fuse. The fuse many times will melt. Some if any fault takes place, no, or if any tree branch is falling on the conductors and line to line short circuit takes place, then the fuse will burn first so that windings are safe. Fuse fault mostly will take place. Yes, fuse. Yes, user decide on. For every examination, these are enough. For every examination, it is required. Okay, completed all of you this figure. Tell me this, all of you completed. Okay. Now observe what is the procedure for this sump-nut test. See, first of all, these two transformers we have to connect. How electrically we are connecting? Magnetically they are separate. One transformer here, one transformer here. In your lab also you will do this test. Two transformers we place. See, primaries. This is transformer A, consider that, and this is transformer B. Both having same voltages, E1 by E2, E1 by E2, same voltages. See, primaries of two transformers connected in parallel only. Now, observe E1, E1, parallelly connected. Now, secondaries. The two secondaries are connected in series. Series, it is connected in series. So, across primaries, we given main supply through auto transformer. This is auto transformer. Across primaries, there is a main supply, and across secondaries, there is a auxiliary supply. So this is called auxiliary supply. Auxiliary supply it is. Auxiliary supply means low voltage supply. Main supply means this is little high voltage supply. This is low voltage supply, auxiliary supply. But both supplies we don't give at a time. This main supply and this auxiliary supply at a time we don't give here. See how we give is they are switches S1, S2. For that reason, we are keeping switches S1, S2. So observe first. Observe first. Switch. First write one point here. Write one point. The primaries of two transformers. Primaries of two transformers are connected in parallel. Are connected in parallel. The primaries of two transformers are connected in parallel, but the secondaries are connected in series, with subtractive polarity. This is important here. Subtractive polarity. So that is I indicated in the diagram, but I did not shown to you. So I will show you now. With subtractive polarity. Two secondaries connected in series with subtractive polarity. What it means is observe. See, when you give supply to primary, no, then secondary side you will put dot notations or dot you will indicate, no, this is the dot here, this is the dot here. Transformer A secondary dot here, transformer B secondary dot here. Now dot connected means additive or subtractive? Subtractive. Additive means what? Opposite polarities. Subtractive means if you join same polarities. So this is subtractive polarity. So why subtractive? You will see now what is the requirement of this. Now observe procedure. Procedure. Observe this. So two cases we are having. First, case one. Case one. In case one, what we do is if S1 is open, S2 is closed. S1 is open, S2 closed. That is case one. Case two is opposite. S1 is closed, S2 is open. Okay, check this. Observe now. S1 open, S2 closed. Observe carefully. Whenever any switch is closed, there is no meaning of supply across that. See, whenever you close S2, is there any use of this auxiliary supply? No, because this voltage gets short circuit. No, actually we don't short circuit voltage. High currents will flow here. What we do is this auto transformer output voltage we make zero, means short circuit nature it is. When you close switch S2, there is no use of this supply. It is unnecessary, not required. Means there is no application of this supply in the transformers. We are not applying this. No use, just. Now S1 open. When S1 is open, you can give this main supply to transformer. Now primaries are in parallel. No, two primaries. A little concentrate. Primaries are in parallel. Now let us increase the voltage slowly. Increase the voltage. Now first of all, when S1 is open, S2 is closed. One test is going on in the two transformers. Which one that is? OC test or SC test? Whenever S1 is open, S2 is closed. Which test is going on in the two transformers? Open circuit test or short circuit test? Tell me this. Okay. So okay. So most of you saying short circuit test. Okay, enough. Most of you saying here short circuit test, but answer is open circuit test. Answer is open circuit test, not short circuit. See why it is. What is meaning of open circuit? Secondary, no current. Secondary open, no. When you give supply to primary, secondary should be open, means zero current in secondary. And what is meaning of short circuit? When you give supply to primary, secondary winding should short circuit and there is a current in that. But observe, when S1 is open, S2 is closed. When S2 is closed, observe carefully. Primary side you are giving supply. Now secondary side there is E2 on transformer A and transformer B also having same magnitude of voltage. And how they are connected in series here? Subtractive nature. If E2 is 200, this is also 200. 200 minus 200, 0. Zero voltage. If voltage is zero in the winding, is any current will flow? No. Current is zero. Whenever voltage is zero in the winding, no current will flow. So current zero in the winding indicates open or short? Open. So open circuit is going on. Now, just like open circuit test, this voltmeter will read some voltage and no load current will flow here. And wattmeter will read the power drawn by transformers. Two transformers are there. This transformer will draw a current I naught. This transformer will draw a current I naught. Now, what is the total ammeter reading I1 here? 2 I naught. And voltmeter will read voltage across transformers. And as they are parallel, same voltage it will show. What is voltage in parallel combination? Same now for two transformers, same only. And this wattmeter also will read power drawn by two transformers. Power drawn by two transformers, W1, W2. Okay. So first write one point here. So S1 open, S2 closed means this is a open circuit test, OC test. OC test it is. Now under this, the ammeter I1 will give 2 I naught and voltmeter will give V naught and wattmeter will give 2 W naught. So in OC test we have three readings, I naught, V naught, W naught. So that is we are writing here. Ammeter I1 in the figure observe, it will read 2 I naught. Two transformers drawing I naught, I naught. Same identical, no? That's why same it is 2 I naught. But voltmeter will show same voltage for both transformer and wattmeter will show power drawn by two transformers. Then from this, if you want no load current of each transformer, you have to take half of that. And if you want voltage across each transformer, that is directly same as voltmeter reading. And power drawn by each transformer is W1 by 2. So this is only you will get in the examination. If you get any numerical type of question also, only this. So they will ask, the ammeter is reading 5 amperes. What is the current drawn by each transformer? Half of that only you have to take, because that meter will read current drawn by two transformers. Okay. This is OC test. Okay. Now in this OC test, which loss is taking place? Iron. So transformer core will heated up here. Okay. Transformer core is heating now mainly. Next, case 2. Binila, does this primary should be LV, sir? So here primary for Sampurna's test, it is not important LV or HV. Anywhere you can give this. So according to the figure, it looks like high voltage side you are giving supply. Anything, whatever it is. Whatever it is, iron loss is taking place because OC test. One side you given supply, other side is open circuit. Okay. Any side you can take. So you can consider primary is LV side only. How I1 is 2 I naught? How W1 is 2 W naught? So clearly I given now here. See the figure. There are two transformers in parallel. This transformer primary drawing I naught, this transformer primary drawing I naught. What is the sum of these two? 2 I naught. So I1 will measure, I1 means ammeter reading. This ammeter will measure current drawn by two transformers. 2 I naught, no, sum of these two. Similarly, W. wattmeter also. Okay, Vaishnavi. Hmm. Because of that reason, we are connecting subtractive polarity. Suppose if you don't connect dot dot here, E2 plus E2 will get additive. Then secondary current is not zero. Then that is not OC test. So in order to get OC test mainly, open circuit test mainly, the secondaries we are connecting as a subtractive polarity. Dot dot is connected. Clear now all of you this one? This is case 1. S1 is open, S2 is closed. OC test is going on in two transformers. Okay. Now case 2. Case 2. Case 2. Opposite to previous. If S1 is closed, S2 is open. Now which test will be there? Short circuit test it is. Now during this we have short circuit test. Observe the figure. Observe the figure. Now S1 is closed. S1 is closed. S2 is open. S2 is open. S2 open. Now when S2 open, you can give auxiliary supply. Now auxiliary supply is in operation. Auxiliary supply you can give. Auxiliary means low voltage. Why low voltage? In short circuit test, how much voltage we need to apply? Low voltage only we need to apply. That's why it is auxiliary supply. And S1 is closed. Now observe important. When S1 is closed, it is this point and this point short circuit. No, means primaries of two transformers acting as a short circuit. Observe, primary of transformer A, primary of transformer B parallel. Across that there is a short circuit. Now which is important? When in parallel, if there is a zero resistance, short circuit means the windings is acting as short circuit. The E1 windings acting as a short circuit here, and you are giving supply to now secondary side. Now here you will give supply. Now as it is short circuit on other side, how much voltage you need to apply? Low voltage. So slowly increase the voltage by observing this ammeter. Now this ammeter should read rated current of this second E2 winding. E2 winding. Okay. Now tell me this, what is the current flowing in two windings, E2 E2? Same current, no, because both are in series. Same current will flow in this. Then I2 will read current drawn by each transformer. I2 equal to ISC only. So you remember short circuit test, same as it is here also. Now when you give supply from auxiliary voltage source, this ammeter I2 will read current drawn by each transformer, ISC. And this wattmeter will read power drawn by two transformers, transformer A, transformer B. So copper loss of two transformers it will measure. And what is voltmeter measurement here? This voltmeter V2 is for two windings or two transformer secondaries E2 E2. Then this voltmeter will measure voltage across transformer A and voltage across transformer B, 2 VSC. Here current is same. Voltmeter reading, ammeter read, wattmeter reading is double because two transformers we connected. So right here one point. During this there is a short circuit of E1 winding E1. See, because of S1 is closed, E1 of two transformers acting as short circuit of windings E1 for both transformers. So now we need to apply voltage from auxiliary supply slowly by observing ammeter, because short circuit test it is. We need to observe ammeter only, rated current, to find rated current. Therefore, Here the ammeter I2 will read rated current of each transformer, ISC only, because series same current, not double, it is same current series. And voltmeter will read voltage across two transformer windings, so that is 2 VSC. Short circuit test, whatever terms we have, that is I'm writing VSC, ISC, WSC. And W2 will read 2 WSC. If you want rated current of each transformer, ISC equal to I2 itself. And if you want voltage across each transformer, VSC equal to half of the voltmeter reading. And if you want copper loss of each transformer, WSC equal to W2 by 2, half of the wattmeter reading. Okay, like this we take. So here copper loss is taking place. Copper loss we are getting in this copper loss. Now which part of transformer heated up? Windings heated up. Previously core heated up. But at a time you don't get both the losses simultaneously. That's why we said simultaneously both the losses will take place, but not at a time, because at a time both the tests are going on. No, only one loss in case one, in other case other loss. Then how we can get exact temperature? Yes, we can get. How it is, uh, first case one, S1 is open, S2 is closed. Okay, during this let us keep like this for some time. Means we no need to hold the switches, just open and leave and keep it is for some time, for 5 minutes. Then iron is heated up. Now after a small time, after 5 minutes, again do opposite. S1 is closed, S2 is open. Then again keep it is for some time, 5 minutes. So once after case one, immediately is the iron gets cooled? No, previously iron heated up. Now when you do case two, copper winding heated up, but at a time the iron will not get cooled. No, there is some heat in the iron. So both temperatures simultaneously will increase. Core and winding simultaneously increases. But in OC and SC test, what happened? In OC test, only iron heated up, but not copper winding. In short circuit test, only copper heated up, but not core. But here both simultaneously heated up. So these two cases you have to perform. Up to what you have to perform? Not one time or two time. Perform continuously like this. Up to what? Up to you get maximum temperature from the transformer by measuring with sensors. Measure the temperature with sensors and check what is the maximum temperature you got. Suppose after 3 hours you got a maximum temperature and further not increasing. That is the maximum rise of the temperature. Based on that, we will decide the capacity. Okay, so make a note. Make a note here. Note. Right, first point. Perform the above two cases. Perform the above two cases. Above two cases up to maximum temperature rise of transformer. Up to maximum temperature rise of transformers. Up to maximum temperature rise of transformers. Due to this, we call, due to this, it is called as, because of the temperature rise, as we are conducting this test as long as you get maximum temperature. That's why we name it is temperature rise test. This test is performed to raise the temperature of transformer. Hence it is called as heat run. Heat run. We are running the test to get heat in the transformer. Heat run test or temperature rise test. Temperature rise test. Okay, so one important point. So run the above procedure continuously as long as you get maximum temperature from transformer. Okay, but there is a drawback in this test. Drawback. So the main drawback is at a time the losses are not taking place in this test. At a time. So when losses will take place? Only in the load test. When both will take place? Only in load test. That's why practically in manufacturing side, Sumner's test mostly they don't do right now. They are doing this load test. Load directly connect. Just now I given one example here previously. See this one. So I said voltage rating is there and you connect directly a load on that and observe for some time. This is very easy. Compared to Sumner's, very easy. Sumner's test required two transformers to do the test. But in this load test, you don't require two transformer, one transformer, whatever you need to decide the rating, that is enough. So load test directly we do. Okay. To find the temperature rise. Right. Second point. This test required two identical transformers. This test requires two identical transformers. Two identical transformers and also the iron and copper loss will not takes place at a time comma it will takes place simultaneously. It will takes place simultaneously means one after other only takes place, not at a time both. It will takes place simultaneously. Okay. Therefore in practical direct load test, write that point. In practical, next line, in practical direct load test is preferred. Direct load test is preferred to find maximum temperature rise of transformer. Direct load test is preferred to find maximum temperature rise of transformer, comma, comma, from which the volt ampere rating of transformer, from which the volt ampere rating of transformer is decided, from which the volt ampere rating of transformer is decided. So from the temperature rise only we decide rating finally. Clear? So this is about Sumner's test. And with this we stop today, and in the tomorrow next class we start the performance parameters of transformer. Okay. Why we need two transformers here means it is invented by Sumners. So you invent one test, then we will put your name. So based on whatever they given Sumners test Sumners, so we are following that here. Okay. Otherwise, if you take single transformer, that is direct load test. Sandeep. That is the procedure given by Sumners. Why two transformers? What I can tell. Yes, subject is easy, but lot of things means what? If you don't know anything already, now it looks like lot of things. Yes, practically we are not using Sumner's test. Practically we are not using because there is drawback now. Two transformers, these are all drawback. Yes, in Sumner's in short circuit test, temperature rise of both we are getting. So any one we will consider any one. Yes, you can use one transformer. That is a load test. That is only I'm saying no load test, that is directly. to find maximum temperature rise from which the volt ampere rating of transformer is decided. Okay. In case 2, I'm giving one more time. See, case 2. S1 is closed. S2 open. Observe the figure. When you close S1, primaries E1, E2, E1, E1 of both transformers shorted. No. See, across the winding, there is a short. Means winding is acting as short circuit only. Okay. Winding is acting as short. Means E1, E1 is acting as short. Now this E2, E2 across that we are giving a supply. Now this is like primary of transformer and this is secondary. So, but E1, E2 I'm not changing, keeping as it is. Anywhere you can give supply. Now you are giving supply to E2 side. Now this winding E1 acting as short. So short circuit test. And for this also current is flowing like this, and this is like a source connected to E2 and E1 is acting as short. Now there is a short circuit test in both transformers. Then we will apply a voltage so that rated current will flow. This I2, we will observe this ammeter I2 so that rated current is flowing. Just like short circuit test, however, we have seen same procedure. Now I2 is flowing here, rated current. Now as current is flowing, rated current, copper loss in transformer A, copper loss in transformer B. This loss is measured by W2. It is measuring losses of two transformers. That's why W2 equal to 2 WS. Similarly, voltmeter is for two transformers. It is across connected. No, the voltmeter will give voltage across two transformers. That is, we have taken VSC is half of that, WSC is half of that. Okay. Mohammed Mabin. No, this is only the drawback in the Sumner's test. Yes, case 1 we should conduct for some time and case 2 for some time. Continued up to you get maximum temperature, not for only one time or two times. Up to you get maximum temperature, you need to perform this. Okay. Yes, back to back. Why we call back to back test? It is Sumner's test. OC test, SC test, back to back we are doing. Back to back, one after other quickly. No need to change any connection, just switch operations. Back to back we are doing. That's why we call back to back test. Okay, Sagar. Oh, Anil Kumar, tell me. Hello, Anil Kumar. Tell me, Anil Kumar.
Sir, I have a doubt. Sir, you told that the switches are not exactly used in Sumner testing, sir, because you currents will flow. Like it's for representation purpose. In Sumner test, the switches S1 and S2 they are only for representation purpose. Because if the switches are used, huge current will flow. So, sir, then how will we obtain a short circuit, sir, across the windings?
Case 2, you are asking?
Yes, sir.
In case 2, when switch S1 is closed and S2 is open, how it is acting as short circuit?
No, sir. I
Uh,
understood that part.
uh,
I'm thinking because in actuality, switches will not be used, no, sir, because you said.
how it is complete main across main supply we have one auto transformer. You make this complete supply to zero.
Okay, so if
Okay.
voltage drop
uh,
difference is zero, then
Zero means
short
short
circuit.
circuit,
Okay, sir.
like that. Actually switches we don't place because if you directly open and switch close now, source is getting short circuit here.
Yes.
To avoid that, we make simultaneously knobs zero and increasing like that. Okay.
Okay. Yes, sir. Thank you.
Tulasi, tell me. Hello.
So good evening, sir.
Tell me.
Sir, in 123, yes, sir.
Hmm.
Sir, there x is 1 by 4, no, sir.
Huh?
Sir, in 123,
Hmm.
sir, x factor we took, no, sir. The full load copper loss with that we have found.
This one.
Yes, sir.
Oh,
Sir, x is 1 by 2 we have taken, no, sir.
1 by 2 because 10 is taken full load, 5 is half full load, no? Half of that.
Okay, sir. So then in 128, yes, sir.
Hmm.
Sir, here when switch 2 is closed,
Hmm.
E1 and E2 are short. Sorry. In S1 is closed, E1 and E2 are short circuit, no, sir.
Not even E2. E1 of transformer A, E1 of transformer B shorted.
Yes, sir. At that
Uh,
time, the voltage induced, I mean, like E2 access
Primary.
prime
Yes,
and
primary.
E1 access secondary, no, sir.
Yes, yes. Just like
Okay,
short circuit test. You remember short circuit procedure for that.
okay, sir. Then how is that W2 is 2 times of
This is
W?
in series, no? This wattmeter will see current is going in this transformer E2, in this transformer E2. So there is some copper loss in this, there is some copper loss in this, and both is measured by this wattmeter only.
Okay, sir. Yes, sir. Got it.
Hmm.
Thank you.
Hello, sir.
Hello, sir.
Tell me, Tulasi.
Sir, in 112, sir.
Tell me. What is doubt here?
Actually, sir, WSC by VA per unit of resistance, sir.
Oh,
Sir, there we use the rated voltage and rated current, sir.
oh. Per unit?
Per unit resistance, second one, sir. Full load copper loss by VA.
Where? This one only?
Yes, sir. First point only, sir.
This one. Full load
Ah,
copper loss by volt ampere rating.
ah.
Because already we know no about this point. Because percentage R is called percentage copper loss. Both are
Okay,
same, no?
okay, sir.
What is the formula for percentage or per unit copper loss? Full load copper loss by volt ampere rating. So that
Volt.
equation directly I written.
Oh,
In volt ampere, we use rated current and
Uh,
rated
the
voltage.
volt ampere means on the nameplate it will be there already. That is we can
Okay,
use.
okay. In 129, sir. In
Oh,
Samplast.
here.
Sir, yes, sir.
Hmm.
I have a got doubt that subtractive polarity we are telling here, sir.
Hmm.
In 131 F, sir, when S2 is closed,
Hmm.
the two E2s will have the same voltage, no, sir. Then they will cancel out, no, sir. 131.
Okay, observe. Whenever, good one. Whenever you use supply to this side, no,
Yes,
then
sir.
polarity is wrong here. This polarity will not come. This is for only when you use primary side supply. They will
Okay.
induce, there we are connecting subtractor. But here when you give supply, current enters here. This is dot. Current enters here. This is dot.
Okay.
Okay, then it will change. So
Okay.
E2 plus E2, na, additive, that voltage is sum of these two.
Yes, sir.
Okay, right.
Okay. Thank you.
hello, sir.
Tell me, Charan.
Sir, in 114 F, sir.
Hmm. Tell me.
Sir, okay, sir, understand. Sir, due to network issues, I did not reason the pages 118 and 119, sir.
Okay, okay, no problem. One.
118 and 119, sir.
Oh, take snapshots. Okay.
Sir, 120 also, sir.
Good evening, sir.
Tell me, Vikram.
Sir, 122.
Tell.
Sir, how will the answer change if the skin effect is considered?
Skin effect.
If this here we are neglecting the skin effect, so if skin effect
Ah.
is considered, then how will the answer change?
Here we no need to consider about skin effect, na, because directly with respect to data we are answering.
So like in question, if it is given that you have to consider skin effect, then how to solve such a question? Sir?
Means if they are given consider skin effect, these are all just unnecessarily they will give to confuse. If you consider skin effect also, what is the problem of skin effect? Then they have to give what is the resistance of solid conductor or whatever the conductor, and due to that skin effect, resistance increased by 1.6 times of RDC. No, so in skin effect concept, you will get this relation RAC. AC resistance is 1.6 times of RDC. Do you remember this?
Yes, sir.
Then you have to multiply, if they given DC resistance, multiply that AC resistance with 1.6. Then you have to find I1 square R, I square R, I square R in both cases. So like that we need to calculate upper loss. But anyhow, you don't get 100% that model. This is just wanted they given.
Thank you, sir.
Okay.
Sir, hello, sir.
Tell me, Tulasi.
Sir, another doubt, sir. Sir, in 115, power transformer means what, sir, particularly?
Power transformer, all this you will get in next efficiency. You will get, we have power transformer, distribution transformer. Power transformer means high voltage rating.
Okay.
Distribution is low voltage rating. So you
Low
get clearly again in next topics.
Okay. Sir, in 131 of Sumner's test. Sir, can you please explain first note points?
First point,
First point, yes, sir.
the two cases. In case one, which loss you are getting? Iron.
Either.
Case two, which loss we are getting?
Copper loss.
Now, if you just perform one time, is the total heat will generate?
No.
That's why perform these two simultaneously, one after other, up to you get maximum temperature from that.
Right. Okay. Okay, thank you, sir.
Good evening, sir.
Tell me, Akash.
Sir, can we say the power consumed while conducting OC test is iron loss, and
Yes.
and during SC test it is only
Yes. Only, not only, because there is a small other losses also there, but negligible there. So mostly we take OC test iron loss, short circuit test copper loss. Okay.
Sir, in SC test, if we conduct, we are short circuiting the secondary side, that is LV. Sir, if we increase the voltage slightly, if we increase the slightly greater voltage, it may will damage.
Yes, because at that VSC small voltage you are getting rated current. So if you little 10 volts also increase, current will increase, no?
Yes,
Then
sir.
it little no problem. Little no problem, but if you increase more voltage, then if it is very high current, no, then the windings overheated. Loss is more, temperatures are more, and then it may damage.
Till that time it can be.
Yes.
Okay, sir. Sir, one more doubt. Sir, can we compare this effect of magnetostriction, that is dislocation of laminations and humming noise?
Yes.
Is it similar to the back EMF caused in a motor or a electric torque generator?
Same. Opposition only, no, that is.
Okay, sir. That's thank you.
Rakesh.
Sir, my doubt cleared, sir.
Okay, right. Next, Bhavani. Mobile. Tell me, Bhavani.
Sir, my doubt is from yesterday's last question.
Tell me.
Last problem. So here there are for finding full load copper losses, we can write the formula I2 square and R0. Sir, where in R02 place we can substitute V2 by I2.
In place
I
of
know.
R02,
Resistance is equal to V by I now. Sir.
V by I, but you should not write V by I because this resistance is total resistance referred to primary. No, secondary resistance also you are transferring to primary.
So we can transfer the current
Hmm.
from secondary to primary also.
Yes, you can transfer. So anyhow, one thing is anyhow, if you find R01 or if you find R02, then if you find I1 square R01 or I2 square R02, you will get same value in both. Check if you want. For any numerical, check this I1 square R01, I2 square R02, loss you will get same. Okay.
I mean, in place of R02, we can substitute V by I. I means it is transferred from secondary to primary.
V by
V by current, sir, where current is
uh,
transferred from secondary to primary.
no, should not write wrong. Don't write like this.
But here resistance is voltage by current. No, sir.
Voltage by current only, but here in transformer, what voltage it is? Primary having voltage V1 and EMF in winding E1. Then there also it depends. No, not only one voltage. In DC case you can write, but not in AC.
Can we transfer both voltage and current from secondary to primary and calculating V by I? Then
Both voltage and current.
transferring from secondary to primary
Uh,
by using K, and we can do the ratio V by I.
okay, you try that. Check once you are getting same or not. Then you will understand.
Okay, okay,
Okay.
sir, I will do.
Any
Okay,
other?
sir, that's it. That's it. Thank you, sir.
Sir,
Tell me, Mohammed.
sir, that last point you just said, na sir, but you didn't wrote
Which one?
that about Sumner's test, sir. Sir, after conducting the two cases, you have given some points.
Which point?
These are, sir, please explain these 2 points and the last third point also.
Third point is which one? Which one I said?
Sir, you said I didn't wrote, sir. I was listening. I was
Regarding
writing.
what I said?
How we decide the KVA rating is.
Okay, that point, no. So there is a drawback in the Sumner's test, no. That's why what is that? Therefore,
Sir,
it is
sir,
preferred.
I am clear about 1 and 2 steps. Please explain after that, sir. I am not. I
Third one.
didn't connect it
Third
to
one.
that point. Yes, sir.
So due to these drawbacks, we are going to load test directly. What is load test? Single transformer we take and load we connect directly on that, and directly we are checking just now whatever example I have shown previously. So based on that maximum temperature rise, we will decide the volt ampere rating of transformers. Load test. So in the last you can write, therefore the load test is preferred practically in order to find the maximum temperature rise of transformer, from which the volt ampere rating is decided.
Okay.
Okay.
Sir, this iron losses and copper losses will not take place at a time. You said, na, sir.
No,
In
Sumner's,
second point.
in this
Yes,
test,
sir.
Case one,
Yes, sir. Same.
case one, case two, we are doing one after other, no, not at a time.
Yes, sir.
So both will not take place at a time simultaneously. One after only they are taking place. This is a drawback for us.
Okay.
That's why load test is best.
Sir, then you said we will determine the maximum temperature rise, na, sir. It means we have to conduct one after the other
One
several
after
times
other,
or only
several
one time?
times, several times, because up to what you get maximum temperature, that may be 2 hours or 3 hours, you have to conduct.
Okay. Sir, page 119, sir. Sir, this question after break, na, sir. Sir, after break, you explained questions, na, sir. At that time, I was not there.
Don't know which one.
Sir, I'm telling, sir. Sir, a 50 hertz transformer draws a short circuit current of 30 amperes. This I've listened, sir. Before this.
Before this means this one.
Okay, sir. Sir, what is this, sir? Which of the following? Sir, please explain this, sir.
second. In a transformer, which of the following statement is correct? What is given based on the options? In OC test, copper loss, short circuit test, core loss. Is it right? Wrong.
Yes.
No, it is wrong. No?
OC test core loss
Second.
short. Yes.
In OC test, current is drawn at high power factor. Is it right? In
No,
OC
low.
test, generally low power factor.
Yes, sir.
So option B only correct.
Okay.
Okay.
Sir, before this, sir.
Before this means this.
This also I didn't even. Sir, please just explain what we have to find. Then I'll try,
Here,
sir.
there is one transformer 230 by 115 and 2 kVA rating. For this
Okay.
transformer, we need to perform OC test, SC test. So there are
Okay.
4 meters in the laboratory. W1,
Okay.
W2, W3, W4. We have to take 2 meters.
Okay.
Then which 2 are suitable for OC and SC respectively. So out of LPF, 1 for OC.
1 for OC out of
Out of
HPF.
HPF, 1 for SC. Now 250 common, 150 common. So only we have to decide by current.
Correct.
Now for OC, low current is enough, no?
Yes, sir.
That's why 5 amps
Low
is
current.
taken. But
For
short
H.
circuit test, high voltage side rated current we got 8.7.
Okay.
To measure the 10 amps meter is required. Okay.
Sir, some basic things, sir.
No,
Sir,
what?
while some basic questions, sir. Sir, in transformer first approximation circuit we have done, there you have mentioned that no load leakage flux is neglected now.
Yes.
But I didn't get that.
Now under no load condition, there is a current in the winding. What is the current? Very small, no load current, I not. And due to that, there is a leakage flux on primary side. How much flux will be leakage? Very, very small flux. No, compared to load current, no load is very, very small. That's why we can neglect a leakage flux under no load condition.
Sir, one more. Sir, in hysteresis and eddy current equations,
Not article. Not article.
hysteresis and eddy current losses equations, that V is the volume of core, na, sir. Sir,
Yes.
in volume of core we have laminations and insulations. Then
Yes.
in cross section area we have discussed like stacking factor like that. Na, sir.
Yes.
Here do we have anything like?
No. Volume means total area into length of the core. Both we have to take the completely.
That is net cross section area or
Gross only.
means laminations plus insulation.
But anyhow, we never take that volume into calculation because nowhere we use that.
Yeah, nowhere we used, but while designing only we have to decide.
Yes, right. There you can consider net, not gross. Because hysteresis loss and eddy current due to flux only, no?
Hysteresis, eddy current.
Both
yes,
due to flux. So flux is in iron, in not insulating. Then AN you have to take.
AN, sir.
Yes, net.
That stacking factor AN only, sir. In volume also same.
Yes, same.
Okay, without insulation.
Yes.
Sir, one more, sir. Sir, that I mu lags V1 by 90 degrees is there, no? Magnetizing current lags. Sir, basically how we drawn that phasor diagram,
That is,
by taking what reference?
Yes. That is due to inductive nature of winding. We considered current lags reactive component, no? That is.
Yes, sir.
Active component means in phase. Reactive component always lags or leads. Why lagging? Inductive nature. Leads means capacitive nature.
Sir, basically to draw power triangle, phasor diagram, which we should start with V1 reference or flux as references.
V1 reference, because I will start from voltage on, because that is only the source now for everything. Okay, that's why I preferred from there.
Sir, V1 is the reference, then flux lags the V1 by 90 degrees.
Yes.
Then I mu will be in phase with flux. Like that we have to explain us.
First I mu, then flux.
First I mu, then flux. Sir, that's why I'm asking the same question, sir. Again, we came to the same point. I mu lags V1 by 90 degrees. Now only you have said, no, sir.
I mu lags V1 by 90. Okay.
And that only why, sir. I thought that first there will be a flux because of that I mu, but you're telling that after I mu we get
See,
flux.
so that sequence I given according to the from the source side I went, then I given that sequence. Actually, flux is there, then current we consider. So some textbooks will take flux is reference there. Based
Yes,
on that, they will take voltage and everything.
yes, sir. I have studied
Yes,
earlier like that, sir.
I know that. I know that. But to draw for everyone easily, I started from voltage source now, so that I taken that sequence for easy purpose.
Sir,
Anything you can follow this.
sir, if LV is near to core, leakage flux is less. How it
Hmm.
affects sir that HV and LV? Because
Because
of
winding will come near to core, no?
that
As much
insulation
as
width,
possible, winding should be very near to core so that maximum flux within the core will be there.
within the, okay.
If you place HV on HV, then more insulation diameter will increase, no?
Yes.
Due to
Sir,
that reason.
the next question is connected to the same point. Sir,
Hmm.
do we ground the core of the transformer or we are assuming at zero potential now?
No, zero potential.
We
This
are
is not
actually grounding or just assuming?
Yes, assuming. Because direct grounding we don't do, no?
Okay. Sir, one more, sir. Sir, please open a new page, sir. Draw core and draw two windings. Draw a core.
Hmm.
Okay, sir. Same.
Tell me.
Sir, on the left side,
Hmm.
take half LV, half H, and the bottom on half HV. Half LV and half HV, sir.
Okay.
This is one type of winding, sir. Another
Ah.
one, sir. In another core.
Okay.
Another.
Hmm.
Sir, you take like draw windings, sir, not that boxes.
Okay.
Draw LV
Hmm.
and above that draw HV.
Okay.
Sir, which one is correct, sir? Do we actually practically wind like this or like this?
Actual like this only.
Second
Second.
one.
But here we are representing statement. This is half LV, half HV this side. But actually like this only we place. Second one only. Okay, one over other we place with insulating material.
Okay, confirm, sir. Sir,
Okay.
that magnet restriction main reasoning is only humming, or sir? In MCQs
Yes.
he'll ask na, sir.
Yes, magnetosection is due to improper core staggering that is causing noise in transformer.
Yes, sir. That would be the main reason or humming, sir.
Yes.
In question, both are given, sir.
Both means
In options.
which magnetosection and
Magnetostriction is due to sorry, humming noise is due to A, magnetostriction, B, loose staggering.
both are correct, na then.
Both are, sir.
Yes, due to loose staggering only, that is what we are getting, and that phenomenon we call core staggering. Okay, that depends on the person whoever will create. We can create the questions like anything, no?
Yes, sir. That's why
in
I
that
got that.
both you will get.
Okay. Sir, please open 83F, sir. Once.
You are from which place?
I'm from ECIL.
Which
Hyderabad.
place? Hyderabad. Okay,
Hyderabad.
okay. Are you completed or studying?
Studying, sir, third year. Completing now. Third year completed. Now going to fourth.
Because our lockdown, we are forgetting what we are studying.
Yes, sir.
Third year or final year.
I'm from diploma, sir. That's why I'm
very good. Diploma students mostly will have good practical knowledge. Which page? 80?
83F. Lens law is there. Okay, not this. I think you have taken another one. Okay, no, sir, not today's class. It's previous class.
Yesterday's only.
2 days before class, sir. I mean,
if you remember page number.
Page 83F, 2 days before. There. Okay.
Maybe it is changed. I changed the pages. Which one? Concept.
Yeah, maybe this one. Sir. Yeah, this one. Sir, in this, if V by F ratio is not constant, sir, the same question, the bottom one, then how to approach, sir? because
then we
he's
cannot, theoretically we cannot approach. Then numerically, if they given any values, then only we can solve that type of question. Otherwise,
Okay.
if they don't say proper values, how can we judge this?
okay. On these type of questions,
Yes.
okay.
Theoretically, there is some questions only we get like this. Otherwise, if they don't say this constant, you cannot answer this question, because how much voltage reduce or how much frequency reduce, that is we don't know, no, properly.
Yes, yes.
Then we cannot answer.
Sir, I have a numerical set. Sir, to separate hysteresis and eddy current losses, we have discussed, sir, after OC test. In that second problem, sir.
Oh, tell me where it is, page number.
OC test. Immediate after OC test.
This is
Before this. Maybe this one.
This
Wait,
one.
sir. Same, sir. Same question. Sir, how we proceeded this question?
Oh, this is given.
No, sir. No, sir. After this, I got this one. The next question. Yeah, this one. This one.
This is
Sir,
simple.
I'm
no?
not clear about percentage resistance and relation, sir.
Did you listen previously copper losses? Percentage R itself, percentage copper loss, no?
I just noted it down, sir. I'm
What
not
is the
understanding.
formula for percentage copper loss? This one. Full load copper loss by volt ampere rating.
Okay.
Okay. From this, we are calculating full load copper loss first. Because
Okay.
percentage R equal to 1, that is copper loss. Calculated full load copper loss.
Okay. Full load.
200 we got. Now we
Yes.
need to find input power, that is sum of output plus losses. Output they given.
Yes.
Losses is mainly 2, iron and copper. Iron loss is there, and copper loss you got 200. But this 200 you should not substitute directly, because this is full load copper loss.
Full load.
And is it mentioned in the output? Is it full load output?
No.
No. That's why we calculated full load current from given data. We got 90.9. Okay. And from the given output, again we calculated current. We got 85.
Okay.
So the output given is less than full load. For 90.9, this is the copper loss. So we calculated copper loss for 85. That is we substituted in the equation.
Okay.
Okay, this one.
Sir, if he is given like 200 by 400, that we should take as E1, E2,
Yes,
na, sir.
E1
But
by
in some
E2.
questions, we can take it as
V1
E1.
by V2 we take some of the questions.
If it is not possible, then we can assume and
V1
take
by
it.
V2, because almost same both are with negligible drop.
Sir, I got one more, sir. This, to find in short circuit test, after to find percentage reactance, percentage resistance, reactance, impedance in SC test, sir. That's second question, sir. There, this one. Sir, I didn't hear this question.
So given VSC 40%. What is VSC means? Voltage under short circuit we apply 40%. What is the 40% of 1000? 400 volts. So we will apply 400, then rated current will flow.
So naturally we have to take on HV only if it's not mentioned.
If it is not mentioned, also HV only.
Okay.
Then according to that, option C is satisfying.
Okay. I didn't wrote that, but now.
Okay. Teja, tell me. Teja.
Sir, I am audible, sir.
I think you only message, no?
Yes, sir. Yes, sir.
Okay, tell me now.
Sir, actually, అదే సార్ ప్రాక్టికల్ గా సెల్ఫ్ ఇండ్యూస్డ్ ఏఎంఎఫ్ మ్యూచువల్ ఇండ్యూస్డ్ ఏఎంఎఫ్ ఇప్పుడు మీరు స్టార్టింగ్ లో చెప్పారు కదా సార్. అందులో ఫస్ట్ మనం సెల్ఫ్ ఇండ్యూస్డ్ ఏఎంఎఫ్ ఫస్ట్ కాయిల్ కి సప్లై ఇచ్చినప్పుడు నెక్స్ట్ సెకండరీ కాయిల్ లో కూడా ఆ లోడ్ కనెక్ట్ చేస్తే లోడ్ కనెక్ట్ అవుతుందని చెప్పారు కదా సార్. సేమ్ ఈఎంఎఫ్ అనేది సెకండ్ మ్యూచువల్ ఇండ్యూస్డ్ ఏఎంఎఫ్ ద్వారా సేమ్ ఈఎంఎఫ్ అనేది ప్రొడ్యూస్ అవుతుందని చెప్పారు కదా సార్.
సేమ్ ఈఎంఎఫ్ కాదు, ఫ్లక్స్ ఈజ్ సేమ్ ఫర్ బోత్. ఈఎంఎఫ్ మ్యాగ్నిట్యూడ్ అనేది టర్న్స్ మీద డిపెండ్ అవుతుంది కదా.
అవును సార్. అవును సార్.
అప్పుడు ఈఎంఎఫ్ చేంజ్ అవ్వచ్చు కదా.
అవును సార్. ఇప్పుడు దాన్ని ప్రాక్టికల్ గా చేయడానికి అవదా సార్?
ప్రాక్టికల్ గా అంటే
ఇప్పుడు ఐరన్ మెటీరియల్ తీసుకొని దానికి 2 వైండింగ్స్ ఉంటాయి కదా సార్. 2 వైర్స్ ని ఇన్సులేషన్ తీసి డైరెక్ట్ గా ఐరన్ మెటీరియల్ కి హలో సార్.
ఇలానా?
ఎస్ సార్, ఎస్ సార్,
టూ కాయిల్స్.
ఎస్ సార్. ఇప్పుడు ఫస్ట్ కాయిల్ కి సప్లై ఇచ్చాను సార్ బై సాకెట్ ద్వారా 240 volts.
బై
ఇప్పుడు 240 volts సాకెట్ కి ఇచ్చింది. సాకెట్ నుంచి సప్లై
240 volts. ఓకే, ఇచ్చావు.
ఇప్పుడు సెకండరీ సర్క్యూట్ కి లోడ్ బల్బ్ అయితే కనెక్ట్ చేసాం సార్.
కనెక్ట్ చేయొచ్చు. ఎందుకంటే సపోజ్ నీకు ఇంట్లోనే ఒక ట్రాన్స్ఫార్మర్ నువ్వు కొనాలి అప్పుడు.
అవును సార్.
అంటే సపోజ్ నీకు హై వోల్టేజ్ కావాలి, ఒక స్టెప్ అప్ ట్రాన్స్ఫార్మర్ తీసుకో, 240 to some 480 డబుల్.
ఓకే
దెన్ యూ కెన్ డూ దిస్. కానీ మన ట్రాన్స్ఫార్మర్ కాస్ట్ ఎక్కువ కదా.
బట్ సార్ ఇక్కడ సేమ్ ఐరన్ కోర్ యూజ్ చేసినా సేమ్ ఇక్కడ బల్బ్ అనేది
సేమ్ వస్తుంది.
బట్ ఈరోజు ప్రాక్టికల్ గా చేస్తే సార్ అక్కడ సాకెట్ నుంచి జస్ట్ స్పార్క్స్ వచ్చి యూజ్ అనేది గ్లో అయింది సార్. బట్ నాకు అర్థం కాలేదు, ఒక అవ్వాలి కదా సార్, గ్లో అవ్వాలి కదా బల్బ్.
గ్లో అవ్వాలి. ఎంత సెకండరీ వోల్టేజ్ ఎంత అది?
సేమ్ టర్న్ సార్. అంటే దీంట్లో
1:1 240 నా రెండు?
సార్
240 అంటే మేబీ యూ మే గెట్ డ్యూ టు సమ్ ప్రాబ్లమ్ ఇన్ ద ట్రాన్స్ఫార్మర్, సమ్ హై వోల్టేజ్ వచ్చి ఉండొచ్చు. సో హై వోల్టేజ్ వస్తే బల్బ్ డ్యామేజ్ అవుద్ది కదా డెఫినెట్లీ లోడ్ అనేది. ఎందుకంటే దట్ బల్బ్ ఈస్ డిజైన్ ఫర్ 220 or 230, బట్ ఇఫ్ మోర్ దాన్ దట్ 270 280 వచ్చినా కూడా బల్బ్ బ్లాస్ట్ అవుతుంది. హలో,
ఇప్పుడు 240 volts ఇచ్చాం కదా సార్.
సో ఇట్ ఈస్ డిస్కనెక్టింగ్.
సార్ గుడ్ ఈవినింగ్ సార్.
టెల్ మీ.
సార్
టెల్ మీ తేజ.
సార్ అదే 240 volts సప్లై ఇచ్చినప్పుడు మనం ఫ్లక్స్ లీకేజ్ ఫ్లక్స్ కూడా మనం కన్సిడర్ చేసుకుంటే 220 volts కానీ
Is it having exact voltage rating like 240?
Hello, good evening, sir.
Tell me now.
Sir, స్వప్న స్టోర్స్ లో ప్రతిసారి టెస్ట్ పర్ఫామ్ చేసేటప్పుడు రేటెడ్ కరెంట్ అని అప్లై చేస్తాం సార్.
ప్రతిసారి అంటే షార్ట్ సర్క్యూట్ లోనే రేటెడ్ కరెంట్ అప్లై చేయాలి.
అవును సార్, షార్ట్ సర్క్యూట్ లోనే రేటెడ్ కరెంట్ అప్లై చేస్తాం సార్. అలా అంటే అందులో టెంపరేచర్ రైజ్ ని తెలుసుకోండి అంటే ఐ మీన్ అది నాకు కొంచెం అర్థం కాలేదు సార్. టెంపరేచర్ రైజ్ చేసుకొని అంటే ఒక టెంపరేచర్ అది కొంచెం
మనకి మాక్సిమం టెంపరేచర్ రైజ్ అనేది ఎంతో తెలియదు కదా మనకి.
ఓకే,
ఆ టెంపరేచర్ రైజ్ ఎంత వస్తుందో తెలుసుకోవడానికి మనం రేటెడ్ కరెంట్ సప్లై చేస్తూ ఈ రెండు కేసెస్ ని ఆపరేట్ చేస్తూ ఉండాలి. అప్ టు మనకి మాక్సిమం టెంపరేచర్ వచ్చే వరకు వీ హావ్ టు ఆపరేట్ దిస్.
ఆఫ్టర్ దట్ అంటే దాని తర్వాత ఏమైనా అంటే
no nothing. Suppose after that maximum temperature rise you got 60, then you can increase still current rating. Suppose you don't know current rating of the transformer, give some current. So దాన్ని ఆపరేట్ చేస్తూ చెక్ చేయండి. సపోజ్ టెంపరేచర్ చాలా లెస్ ఉంది, తక్కువ ఉంది, then you can increase some more current.
ఓకే,
then heat again increase అవుతుంది, again ఆపరేట్ చేయాలి. సో అలా ఆపరేట్ చేసుకుంటూ పోవాలి. సో బెటర్ దాన్ దట్ లోడ్ టెస్ట్ ఈస్ బెస్ట్. సంప్నస్ టెస్ట్ కంటే లోడ్ టెస్ట్ అనేది బెస్ట్.
దట్స్ ఇట్, నథింగ్. థాంక్యూ.
Hello sir, good evening sir.
Rameshwari, tell me.
Sir, once open 115 sir. 150. Sir, why B option is not correct sir?
The voltage of 16 volt appears across short circuited secondaries. Across secondary, when you short circuit here, what is the terminal voltage here? 0, no?
Okay.
That's why.
Sir,
No voltage will appear there, 0.
Sir, in case 1 sir, last Sampan's test once explain sir, case 1.
This one?
Yes sir, case 1.
When you close switch S2 and S1 is open,
S1, S2 closed.
S1 open, S2 closed.
Yes,
So
sir.
whenever S2 is closed, you can consider that these two windings are like this. This is E2, this is E2, S2 closed. This is
Okay,
E2,
sir.
this is E2. Now how we connected these two? Subtract.
Yes, sir.
Then what is the potential difference between our additive? What is the difference? E2 minus E2. No,
Yes, sir.
subtraction. So both are same voltages. What is E2 minus E2? 0. If
0.
voltage is 0, any current will flow in secondary? No current.
No, sir.
That's why it is open circuit.
Okay.
Then as it is open circuit, now primary side you need to give rated voltage. So using this main supply and auto transformer, give rated voltage by observing voltmeter.
Yes, sir.
So that voltage will apply for both transformers because both are in parallel primaries.
Yes, sir.
Then this transformer primary will draw a no load current, OC test. This transformer also is drawing no load current.
Okay, sir.
Okay, OC test for two tests is going on at a time. Then I1 will measure, ammeter will measure current of two transformers. No, or what is the current here? 2 I0. Now who will measure that current? Ammeter.
Sir, in second wattmeter there is no current, sir. Then how W2 is working, sir? Then how it
See, now
detects the current?
in case 1 there is no W2. We are not taking W2, I2, V2. This 2 I given for case 2 only. These meters will work for case 2.
అంటే ఒక కేసులో ఇంకొక వాట్మీటర్ పనిచేయదా సార్?
Yes.
ఓకే సార్, థ్యాంక్ యూ సార్.
Good evening, sir.
Jay, tell me. Tell me, Ajay.
Good evening, sir.
Good evening. Tell me.
Sir, I did not understand in open circuit test percentage of R naught X naught. You wrote now, sir. Due to the network problem, I did not listen, sir.
Short circuit test or
Hello?
open circuit?
Short circuit test, sir.
Which one percentage are?
Yes, sir. In per unit you wrote now, sir.
Okay. So percentage R means percentage copper loss only, no? Then what is the formula for per unit or percentage copper loss? That formula I written first. Full load copper loss by volt ampere.
That form. Yes, sir.
Full load copper loss means what wattmeter reading itself copper loss na here in the test.
Yes, sir.
That's why I substituted WSA. Divided by rating
Okay.
will be there on the nameplate. That is I substitute. Then you
Okay.
get percentage R and Z01 from this equation. Percentage Z.
Okay, sir.
Then percentage X. Okay.
Sir, okay, sir. In general, in VSC by
VSC by
VSC by E1 is equal to Z is equal to per unit Z na, sir.
Yeah, yes, per unit impedance.
Yes, sir. Per unit impedance, sir.
Oh.
Sir, actually, VA both are in voltage.
Yes, that is only the per unit definition. Per unit definition is what? Actual by base, both in same voltage. If you write numerator, denominator also voltage. Or per unit current. What is per unit current? Actual current by base current. Same units. Anything you can take in per unit, either voltage, current, resistance, anything.
Okay.
Okay.
Sir. But it, sir, here also in voltage form only, na, sir. But
Which
how
one?
can you?
Which one?
Same, sir. VSC by E1 is equal to per unit Z. How? Why we could not write
per unit voltage. Okay. Here, mainly we are not going with VSC by E1. We are going with this equation. This is we written as per unit impedance. That is we are getting as VSC by E1. Both are same here. Okay.
Okay, sir.
So same per unit impedance we are calculating in terms of voltage. Per unit impedance means what? Per unit voltage drop due to impedance. Voltage drop due to impedance. That is also voltage only, no?
Yes, sir.
That is we are writing in terms of this VSC directly.
Okay, sir.
Okay, good.
that's also, sir, in Sampurna's test is there, na, sir. Sir, that test is why can't we use for both normal open circuit and short circuit test, sir?
We are using now. Why can't we use?
Yes, sir. In general, without directly, we can use this test now.
Not understand. Without using OCSC, we can use directly this. Yes, we can use. Here also you are getting whatever you are getting in OC and SC test. Observe. Case 1 is OC test. Case 2 is SC test. Same iron and copper loss you are calculating here also.
Yes, sir.
But the main problem in OC and SC is only one loss there, but here two losses, one after other, quickly. That's why we are calling back to back. Okay, right.
That's all. Thank you, sir.
This I'm stopping for today, and tomorrow we meet in the same time. Good night.